everybody in the room and on Teams can see the slides. So let me just preface this by saying this is a new lesson in my stats and data science curriculum. So you all are guinea pigs in a way, and every now and then, even though I think I've tested this thing pretty thoroughly, you know, we notice things on the first time it goes live, and you know, sometimes things don't work with the code exactly the way I anticipated. So please do understand if that happens. But let's just go and see how we do. So we're going to talk about missing data today, and we're going to cover describing conceptually what missing data is, why it is can be problematic if you do not properly account for what data are missing and why, and yeah, then what you can do to alleviate that problem. That's the main topic for today. And just to give you an idea of the learning objectives today, I should point out the way these lessons typically work is obviously we only have a couple of hours here, so we're going to just scratch the surface of some of the techniques that are out there and give you the big picture if you want to really get into the implementation. I'm going to give you examples and we'll work through some examples of implementation, but we might gloss over some details and some of the different options, and I can't cover every possible use case in this short lesson. So if you later have a more detailed or complicated situation with your missing data, I'm happy to consult with you on that. But what we will cover conceptually is different kinds of missing data. What happens, like I said, if you ignore missing data, how missing data contributes to uncertainty in the inferences and conclusions we're trying to draw from data, and giving you a bit of a menu of options for addressing that and how to decide which one is appropriate in a particular case. And in terms of practical skills, we're going to look at making some simple visualizations of missing data, graphs and tables. We're going to learn about imputation. You may not have heard that term, but I'll explain what it means later on. And we're going to go from simpler imputation methods to more formal statistical methods incorporating multiple imputation, which allows us to formally account for the uncertainty due to missing data and propagate that uncertainty forward into our final confidence intervals and estimates of parameters in our statistical models, which I think is pretty cool. So let's first, I think it's safe to say that anywhere you have data, you're going to have missing data. Almost every real life data set has values missing for one reason or another. Why can that be a problem? Oh, please feel free to interrupt anytime you have questions. Just yell out if you're in person, or if you're on Teams, feel free to unmute or ask a question in the chat. If I miss it, hopefully Grant will point it out to me. So data can be missing for many different reasons, and those reasons are very context dependent, and they're also field dependent. Depending on what kind of data you work with, there's different probability of data being missing for different reasons. So let's throw out some audience participation. If anybody can give me some ideas or from your own experience of why a data set might have a missing value in it.
Equipment failure.
Okay, yep.
Loss of access to field site.
Yep, so these are sort of logistical reasons. Anything else? Anyone on Teams want to throw one in the chat?
Have you identified it as an outlier?
Okay, yes, so that's sort of
Point in the time series.
a data-driven reason. Errors in sequencing data. Yep, so these are all very good reasons, and I kind of have some reasons myself, some of which overlap with what you all said. Obviously, instrumentation or equipment failure, or the data was not collected for some particular reason. Like if you have daily time series data, but there's some interruption like a holiday or something like that. Attrition is a common example of missing data. So this could be, you're measuring biomass of a plant after on a certain day, but some of the plants died before that day. That is also, in a way, a missing value. And obviously data records could be lost for any number of reasons. So those are, and obviously that's not an exhaustive list. Those are just some possible examples of why you might have missing data. And here are some other, a little bit more nuanced reasons. There might be some cases where you cannot record a datum for some subjects, like if you have a trait like the length of the longest petal, but a plant doesn't produce flowers for whatever reason, then you're not going to have a length value for that individual. Also, just intrinsically, some instruments or ways of measuring things have limits of detection. So a concentration of an element may be too low to capture from some particular assay, or, your thermometer can't measure temperatures above a certain temperature, things like that. And then we mentioned outliers, but also like data that doesn't fit in some assumption of a statistical model. For example, if you have zeros in your data and then you log transform that data, logarithm of 0 is not defined. So that's yes, that's another way that we can sort of interpret that as missing data, but it's slightly different than a case of it not being measured at all. There is sort of a taxonomy or categorization of missing data. That this was originally proposed by Donald Rubin, who we'll talk about again later today. And he thought about the processes that determine the probability of a data point being missing. And there's sort of three categories he came up with that have little acronyms: MCAR, missing completely at random, missing at random, and missing not at random. What does that mean? Because you'll see this if you ever look at the missing data literature, these crop up a lot. So missing completely at random means for any given data point in the data set, the probability of that data being a missing value or not is equal for any of them. And so this is sort of the simplest and least problematic kind of missing data, because you don't really have to account for any biases resulting from that, because there's no confounding factors. Any given data point has an equal probability of being missing of any other. Obviously, the worst thing about that is it reduces your sample size if you have a lot of missing values, but it doesn't bias the estimate of the mean or any other parameter you might calculate. It's just random sampling error of which ones are missing, which ones aren't. So this would be, if you can get away with assuming that data are missing completely at random, you really don't have to do much. You just have to say, well, a few values are missing, and that's that. But in reality, data are often not missing completely at random, and that's where these other techniques come into play. Missing at random, so that may seem missing completely at random versus missing at random. That seems like, what's the difference there? Well, if data are missing at random, there is a different probability of data being missing or not, but that probability varies by some known variable or group we have in our data. If our instrument is more likely to fail on a rainy day, but we have data on rainfall or something, we can actually model the probability of missingness for any given data point. We actually know the underlying reason why it's missing, although it's still random. It's only a probabilistic process, but we understand why it's missing. Now, this can introduce biases in our conclusions, but we can use that information that we have to model the missing data process. And most standard methods that we're going to talk about today for dealing with missing data assume missing at random, that we the probability of missing this may vary, but we can account for it with information that we have. And missing not at random would be the final and sort of most pathological kind of missing data. That's where the probability of being missing varies, but we don't have information of why that might be the case. And, you know, or it's correlated with some outcome variable that we're trying to make inference about. Like if you have a survey with where you survey people and then follow up with them later, maybe people, and you're trying to measure the strength of their opinion, but people without a strong opinion are less likely to follow up. So that the two things are correlated. So it's missing not at random. Or if you're trying to measure disease resistance of some sort of phenotype in plants, but the less resistant genotypes are more likely to die before the end of the study, their phenotypes are missing, but that's what we're actually trying to measure is their level of resistance. So it's correlated with the probability of being missing is correlated with the outcome that we're trying to measure. So that is problematic and it causes a lot of bias. Any questions so far on any of this? It's all a little abstract and we'll get into the hands-on part soon. I won't just talk at you all day. This is just for intro. Another situation that I was actually talking to some folks here yesterday about is censoring, and that is a specific kind of missing not at random pattern where a data point is missing if it's above or below a threshold, like we were talking about with limit of detection of an instrument, or if a subject dies or is removed from the study before if we're trying to measure survival or some outcome at the end, but it died before that. And again, this is biasing of the results because if you only measure the final biomass or whatever it is on individuals that are still alive, you are essentially statistically conditioning on whether they survive without intending to do so, and that biases your results. You know, that's where you can get paradoxical situations like finding that that smokers are healthier than non-smokers, because if you measure their health at an advanced age, the smokers, many of them have already died and they're removed from the data set, and only really healthy smokers are left. So you can get opposite correlations, for example, than you would expect because of this bias in missing values. And I did want to mention something about replicates or data being missing from design experiments, because I know a lot of people at ARS use, you know, block design and things like that for their design experiments in the lab or field. Like if one of your plots in a randomized complete block design is destroyed or skipped or not measured for whatever reason. Again, this is not ideal. Obviously, you don't want to lose data because you're losing sample size and statistical power, but just from a analysis standpoint, it's not a problem as long as we can assume the data was missing at random. You skipped a plot. Essentially, it was just random which one was destroyed or a tree fell on or whatever. It's random with respect to the outcome you're trying to measure. And it doesn't really mess up your analysis that much, because if you're using a mixed model approach, it does not require data to be perfectly balanced. So you don't have to, you know, if you lost like one plot from that replicate, you don't have to get rid of the entire rest of the replicate just to make your data be balanced. It can determine, there's different sums of square methods for F-tests if you're doing ANOVA that are sensitive to unbalanced data, but it's just something to be cognizant of. But it's not really a problem if some data are missing from a design experiment, as long as it's at random and you account for it. Because again, if data are missing completely at random, it doesn't bias the final conclusion. Okay, so that was sort of the conceptual background before we delve into the hands-on portion, for which we will be using our statistical software to look at missing data. So I think what we're going to do now is take a break from the slides and help everybody get configured to make sure they can run all this code along with me, either on Cynet or on, if you have R installed on your own PC, you're also welcome to use that and not log into Cynet. So what I'm going to do is I will stop sharing these slides, and then I'll show you how to. Well, first we'll do for the people that are going to use Cynet, since I think everybody that's here either said they're going to run it on their own machine or gave me their Cynet account. So I've added everyone's Cynet username to the list of users that have access to the pre-installed packages and data examples for this class. So we're going to get everyone set up on Cynet first, and then Grant can help with that. And then if people are running it on their own machine and need help, either I or Grant will help you. Let's see, so. I guess I'll just share this screen here. Okay, so everyone also should have been sent the link to the course materials for all the lessons we're going to do this week. That is hosted on my my SEA stats page on GitHub Pages, usda-ree-ars.github.io/SEA stats/MS2026 is the URL there. You don't necessarily have to go to that in your browser, but that's FYI. And we have information on here for how to connect to Cynet and get configured. So let's all together walk through the process and get that done. So what you need to do is go to this series on demand here. You can either go to there's the URL for it in the bottom left. Go to that, and then you're going to have to sign in with your credentials. So I'll give everybody a minute to do that, and then we'll once everybody gets connected, yeah, I'll just give a minute for that, and then I'll show you how to start a job, which is essentially requesting some computing resources for a certain amount of time. And then once we get that started, I will show you how to copy the course materials from the shared directory into your own personal temporary directory on the server. And thank you, Grant, for putting that info in the chat as well. Are people here able to sign in to Series on Demand? Has everyone, or some people at least have gotten to that point? So you should see this. And once you get into Series on Demand, there's a drop-down menu that says Interactive Apps at the top. And you can go and click on RStudio Server. And again, if people, remote participants, are stuck, please let me know in the chat. And I'll go through this multiple times if needed. So, okay, once you get into the RStudio Server page, you can select an account under which to run the job. So I have basically set up this SEA stats account to do all the training workshops from. So you're going to select that from your drop-down menu. Series is the name of the queue. Yep, this one isn't necessary. We're gonna use R 4.4.1, since that's the version that all the packages were installed under. 4 hours should be plenty for today, should, just a little more than you might need. You can select 2 cores. I forget what I said this 4 gigs of RAM should be more than enough for the small amount of computing that we're gonna be doing today. And sometimes these reservation things actually cause more trouble than they're worth, but I have requested Scinet to reserve some processors for us to use just for this workshop so that we'll go to the top of the line and not have to wait for our jobs to start. So the way that you get on that reservation is in this optional Slurm arguments box, type -- reservation equals MS 2026, capital N, capital S 2026. So -- reservation equals capital MS 2026 with no spaces in there. And then you should hit this blue button and hopefully it'll all work. Good, so then you'll see this, and then you have to give it a second to start the session. And after a few seconds, this blue button should come up that says connect to RStudio server. And once it does, go ahead and click on that. Have you all been able to do that? Great. Okay, that will probably not show up for you. I have this set to dark mode, by the way. I think maybe it actually is a little easier to see on the shared screen if it's not dark mode. So let me change that. There we go. Okay, and now the next thing we're going to do, this step only has to be done once. If you're going to participate in multiple workshops this week, all the materials for Tuesday and Thursday are in the same shared directory that we're going to copy together. So what you need to do is go, Grant, hopefully, can you paste this into the chat as well? But this, if you scroll down on this MS 2026 page, there's 2 lines of code here. What this does is within your own temporary 90-day data space, it will create a directory for this workshop, and then it will copy the example data and code worksheets from the location that I've put them on into your own personal directory. So, and Graham's also put this in the Teams chat. So you just highlight these 2 lines, copy them, okay? And then go back to RStudio server. And then you're gonna, not in the console, but you're gonna go to this terminal tab because these are system commands. Go to the terminal tab and right click, hit paste, and hit enter. And that will more or less instantaneously copy the example files into your own space so that you can fill out the worksheet as we go. How's everyone doing on that? Okay, looks like we're getting some thumbs up on Teams, so people are getting that done. Does anybody still need time in here, or is everyone good? Cool. Sorry, I just don't want to get anyone left behind here. So, and now the next thing we're going to have to do is basically what we have done is copy the data over, but now the data are in a project for what we're gonna do is open what's called a project within RStudio, which is like a way to manage different tasks that you're doing on RStudio. And so all the example data, and not to mention R uses a lot of packages like libraries. So all the packages, the project also includes a pointer to where those packages are installed. So we have to open that project for you to be able to run the code that we're going to do for today. So the way we're going to have to do that is by going to this Files tab, which should be in your bottom right, and you have to click on this Go to Directory, which is this little ellipsis right here. Click on that. And then you're going to have to type in this path exactly as I do it. /90day data. So first a /, then 90-day data /shared / your username. So I'm going to type Quentin Reed, but you type your username in here /MS2026. And then hit OK or enter. I'll leave that up for a second. Lavanya, what do you want me to show again? I'm sorry.
How to go to the path to folder?
Okay, yes. So this is I clicked on this little 3 dots right here on the right. Once you click on that, this window will open. Did you get that?
I didn't see the 3 dots. Like right click it?
Just click on it, not right click, just click on it. And then this go to folder will open up.
Oh, MK directory. Okay.
Let me know whether you get that. I'll you have it, Lavanya?
No.
Okay, hopefully Grant can help you in a second. He's helping someone here in person as well, so.
Okay,
But
that's
I
fine.
want to go ahead while people are still here. Let me just cancel this and then yeah, so once you just go over here and click on this in the Files tab. You might have to, if you're in some other tab here, you have to click on Files, get this Files tab to appear. And then right underneath the refresh up here, there's should be right on the middle right of your screen, it says Go to Directory. So I'm going to click on that. Okay. And then I'm going to type the path. MS-26 and enter. The order started here. And then once you're there, all you have to do is just click once on this rproj file right here. Just click on that a single time. And say yes when it asks you to open the project. And it will have to restart R. But then you should see your screen should look more or less identical to mine, where you have this folder that says data and folder that says worksheets. Anyone need help getting to that point?
If you use your own computer, do you have to like recreate that?
Yeah, so I didn't.
That structure?
What you are going to need to do if you're using your own computer is install the R packages that we need for today, plus download the worksheets. And the worksheets are on the wait, first let me just finish this and then I'll show how one would do that if you're using your own machine. So yeah, if you click on this worksheets folder to open it up once you're inside the project, again, and if you're in the project, you'll know because it'll say MS 2026 up here. That's how you know that you are inside of the project. Click on worksheets and open up this dealing with missing data worksheet. Click on that one time. It will open I call it a worksheet, but basically what it is a R script with some of the code strategically missing so that you can, well, I didn't come up with this way of doing it, but I think it works really well for these things. If I would just show you code and make you type it in without giving you anything to start from, you would get lost and fall behind. But if I just gave you code and said copy paste, you wouldn't learn because your fingers wouldn't learn how to actually type in the code. So this is a bit of a compromise. There's a few blanks missing from the code, and you can fill those in. But also, I just want to point out that if you go back up a level in this here, I also have the worksheets with the blanks filled in. So all the code is complete and filled in there right here. But I do not recommend you just running the code right off of that. Even though it will work, you won't learn. So, but if you fall behind, you can open this one up with the blanks filled in as another script, and everything's already filled in there that we're gonna do. Yes, it's quite a bit, but I'll just close that for now. So yeah, that's yes. So Lavanya, you're still stuck. We're having trouble getting the break room set up. Okay, yep. So Grant is going to we'll quickly create a Zoom meeting that you can just join Lavanya, and he'll get on. Grant will get on that with you and help you get unstuck. Thanks, Grant. Okay, so while he's doing that, I'll just show you Eddie and anyone else who needs it. If you go back to the lesson materials page and scroll down, let's see, where is it? Yeah, so here are the two example data sets
I have those.
that you would have to, hopefully, if you're doing this, you understand how to save it to a file path and then enter that file path in when it's time to import the data. But I will help you with that as the time comes if you need it. That's where those are. And if you haven't done it yet, if you're running R, your own version of R, if you go up here where it says option 2, install the software and run the code on your own local computer, and open up that. Install R in RStudio. Obviously, got to do that if you haven't done it yet, because RStudio requires admin. So if you haven't done that yet, it might be hard for you to do it real quick. But if you need to install the packages for today, I've put a install packages command here that you can copy and paste and run in the console of your own R installation, and it will install all the packages needed for today and Thursday.
So I did that yesterday, and
Great.
it downloaded those and the dependencies, but then, after it was done, it says binaries are saved in some kind of temporary folder. So I don't know whether they're
Yes,
truly installed or not.
yeah, but the package installation directory goes to a permanent folder. So
Okay.
yeah, so you should be good. Okay, I'll just here. Why don't we just take like a 5-minute break, and I mean, people can just go to the bathroom and stuff if they need to, because some people are still getting set up.
Okay.
It's better to just not let anyone fall behind now. So we'll just take a 5-minute break. I'm gonna run to the restroom myself, but I'll be back and help anyone who is stuck.
Okay. And would you advise to create a project for this in our studio? Or
You don't have to. You don't have to. The main reason I'm doing it on here is because the packages are installed within there.
I've got.
Yeah.
I don't even know if I can do it.
So I only have one purpose for emergency one.
So I've got one branch too that I'm running on. well, I mean, there's several, but there's one that is for, he's gonna take something like that, it's on the truck, it's just, it's too loud, it's just like two power line.
Bucket truck, maybe a whole project.
Or whatever it could be.
I didn't know.
You need to plug this line tree, but that costs a fortune too.
I thought about using a mountain climber and going up an adjacent tree and trying to.
That's what bad. I use my climbers to help get cat down.
Yeah.
But you know, badly, past that first limb though,
Right.
I'm not going around a limb. I mean, I
Yeah.
can see where it'd be possible, but I'm not doing that. My desire to be climbing up high was done.
I'm
Long since going.
Oh, yeah. When I first got climbing, all of a sudden, the valley going the tree, and all of a sudden, it just slid down the tree. That's crazy.
I never.
didn't it? Oh, it did, absolutely. Nothing worse than falling. I know when it's gonna fall.
So what, and that's what they do, that's all they would need, is the motorcycle machine.
Really?
And on the V, it's. That. But I had them that just had plastic or different things. I'm
Okay. We're still on break for a couple minutes, but if anybody on Teams, needs help, please let me know in the chat and I can help get set up. Otherwise, we'll start back up again in 3 minutes at 9:48.
Probably a few of us, we have a conference call at 10
Okay,
for the national program meeting. So,
yes, that is, a national program leader is more important than me, so, yeah.
Yeah, we're starting,
accepting.
writing or a new road.
And no one knows the process and all of that, so,
No.
yeah,
It's new, so.
yes, yep. Good luck with that.
Uno más.
Did you already tell him that you're ducking out?
Yeah.
Okay, I'm also,
Yeah, I was about to say,
Oh, yeah, no, we're,
today or Thursday, I'll just work with whichever one of y'all to figure out
Well,
what.
they have scheduled like an hour.
Those emails are
meeting. That's pretty.
Yeah, that would go.
Because I cannot
Position together, but I don't know.
yeah, I really hope it's not.
Okay.
too much.
I just did it, let's talk to me.
Do you think it matters what room I duck in? Can I just?
Thank you.
Oh, yeah.
Thank you.
Okay.
I mean, if half the people are leaving, we can like, I mean, if it's gonna be a
No,
long.
I
meeting,
think it's just a.
Okay.
You're gonna say.
Yeah, I'm.
All right, so I won't be talking to a completely empty room and
Right, yeah.
that's good,
Yeah.
okay, awesome,
I'm gonna attend because I have to write.
for sure, yeah, no, I.
Check plan for.
Yeah,
Yeah, same.
Yes,
She's
I'm
fine too.
not offended. Okay, so I think everybody is good, so thank you for your patience, everyone. We'll try to do a little science before the NPO meeting there. Okay, so I'll get back into it and continue to go through. So what we're gonna do before we start to figure out how to solve the problem of missing data, we're just gonna look at kind of from a more programming standpoint, how the R, the statistical programming language, deals with missing values and how they are formatted, which you kind of need to understand before we figure out how to address the issue. So, yeah, basically, we'll go ahead and also, this is where we can make sure this part works. If you go into the, your RStudio server window, I haven't made any blanks for you to fill in here. If you would highlight the entire block of code that includes all the library calls, which loads packages into your working environment. And then you can either click on the run button once you have it highlighted, or you can hit Control Enter or Command Enter to run that. So we're gonna do that. And if you have the project set up correctly, all the packages should load. If you get an error, that means you didn't get into the project correctly, so this would be a good time to let me know if you got an error. I mean, you'll see a lot of messages about package on load, and so there's conflicting function names of being packaged and stuff, but okay, Lavanya has got an error. It may well be that you did not open the project. Grant, hopefully you can help her out.
I'm getting several errors.
Okay,
I've at
Yeah, I
least
can-
getting
I
a
can
lot of
just
red
take a look.
language.
yeah, yeah, those are just memories. Yeah.
Empty.
That just makes them nice.
Okay, thank you.
See the angry red?
Just-
Yeah.
And then sounds like-
Yeah, for some reason, the
Sound good.
default color scheme has red for everything, errors and just like diagnostics, so, yeah.
Not particularly helpful.
No, it's not.
No, but the battery, not. Top battery doesn't. I can say that. This is,
Okay,
I just wanted to see. I use one.
so once, hopefully most people can get those going. I'll just forge ahead here. While people are getting everything going. Across all data types in R, there is a special code that represents missing values, and that is NA, which stands for not available. And it is used across all data types. Okay, good. So Lavanya, it looks like it was just the messages that are talking about conflicts between function names, and it was not an error. So all good. Across, R has various data types, numeric, character data, factor, and logical, among others. Any of those can have missing values, and every time, no matter what the data type is, NA is what will appear if there's a missing value in a vector of values of that data type. And oh yeah, sorry, this so before we go ahead, and I forgot about this, before we go to that part, you're also going to want to run all this code starting at line 30 and going down to line 65. Just highlight all that and hit Control Enter, and that's just some custom plotting functions that I define to make visualizations of the missing data if you want to recreate them on your side. You're just going to run all of that. So highlight everything from line 30 to line 63 and hit Control Enter again or click Run, and it will run all of that. We're not going to get into how to create these special visualizations today because that's a little technical in terms of the code. Yes, that's right. You do not need to copy and paste code to run it. It should all be available to you in the worksheet. Okay. Now, let's look at how R deals with missing values. We're finally going to actually learn something here about an hour in, but the pace of knowledge will pick up dramatically from here on out, I promise. Okay, so here we're going to create a vector called X. A vector is essentially a list of values, all of which have the same data type. And you create a vector by using the C function, which stands for combine, and individual elements within the vector are separated by commas. And you see here I put 3 dots. Anytime you see 3 dots, an ellipsis in here, that's a blank that you're going to have to replace those 3 dots with the actual code. And so you can highlight those 3 dots and replace them with NA in capitals. And that will, and then now if you have your cursor on a line within RStudio, you don't have to highlight the line. If you just have your cursor on a line and hit Control Enter or Command Enter, it will execute just that single line of code. And we have now created a vector called X, which is 5 elements long. It has 4 integers and 1 missing value in it. Okay? So the next thing you're going to do is look at what happens when we try to calculate summary statistics on a vector that contains 1 or more NAs, 1 or more missing values. For example, mean. What do you think will happen if we type mean parentheses X to calculate the mean of X? You can see that some auto completion help comes up when you type in mean, but if you hit escape, you can make that go away. If we hit Control Enter while our cursor is on the line that says mean of X, here we see we get NA. Now, this is frustrating sometimes for people that are just getting started out with R, where if you have, see y'all soon.
Yeah.
If you have a million values, but even one of them is missing, and you try to take the mean is also going to be a missing value. And some people are annoyed by that. It's like, well, why doesn't it just automatically get rid of the missing value and calculate the mean of the non-missing values? But I think all in all, it is desirable for it to do it this way by default because it doesn't do anything unexpected. Like it will, this is the expectation that the expectation of mean by default is that you're going to get no missing values in there. If a value is missing for some reason that happened in the code along the way that you weren't expecting, then you'll get that NA and realize that there's a problem that you have to deal with. So by default, I think it's a good thing that just mean of X produces a missing value if there's any missing values in there. And the same goes for sum and median and other summary statistics. If you run those lines, I'm going to run line 71 here. Yeah, they all produce NA if there's even one NA in the data.
So Quentin, just to.
Yes.
Your MATLAB uses NaN instead of NA, and there's a whole class, there's like nan mean, nan sum, and every time you do it, it says this is not recommended, don't do this.
I see, it gives you a warning. Okay, yeah,
It's,
yeah. Well,
just ignore it and go on and calculate things, so.
R also has an NaN. NA is different than NaN.
Oh, okay.
NaN is the result of a computation that is undefined. Like if you took the log of 0,
Right.
you get NaN, not NA, because
Yeah.
it's not a missing value, it's an undefined result of a computation. So actually that is, that's different than,
Okay, sure.
or no, maybe log of 0 will produce, does it produce negative infinity or, well, here, let me type it and see
The same idea, something that you ought to pay attention to, but it will ignore it for you.
exactly. But yeah, you get negative infinity, but that's actually different. NaN, I can't think of the top of my head of how you would produce one, but you can also produce NaN from some undefined computations. Yep. Now, how do we, let's say we did want to calculate the mean of all non-missing elements of the vector X. Well, a lot of the summary statistic functions, such as mean, have an argument na.rm, which means remove NA values. And by default, it is set to false, meaning it will not remove the NA values and it'll give you a missing value. But if we override that default and set it to true, it will remove the missing values before it calculates the mean. So that's na.rm in all lowercase equals true in capitals. True is a special logical flag in R. And if we run that, I'll hit Control Enter there. We get 3. The mean of 1, 2, 4, and 5 is 3. And I've also, just for the sake of example, we can do the same for sum and median. Control Enter. There's the sum of the numbers. There's the median. And now that's for sort of simple univariate summary statistics, how you would deal with it. what does, what about a lot of the statistical modeling packages? You know, the mean, sum, and median are included in base R, but, you know, the beauty and the curse of R is that it's an open source language and all the packages are written by different people. And each one of them has its own, unfortunately, its own non-standard way of dealing with missing values. Like if you're a SAS user, there's like a top-down regulation of all their procedures. So all statistical modeling procedures in SAS deal with missing values in the same way, which is nice. I mean, you know, that's the benefit of using SAS. So, but with R, the sort of drawback is that you have to learn idiosyncratically what each of the packages do in terms of missing values. So we're going to look at a common mixed model package in R called GLMN-TMB and look at how it deals with missing values. So first, we're going to look at what happens when you fit a mixed model without missing values. And we're going to first, so there's a package called AgriDat that has a bunch of example data sets. And that's where this example data set comes from. So if we run line 78, hit Control Enter, and it will load this pre-created example data set into our environment. And then if you basically, I won't go into the details of this, but this is fitting a mixed model to the yield variable, to some sort of yield variable in a data set about beets, and a fertilization treatment is the fixed effect, and there's replicate blocks in the experiment, so that's a random effect. Pretty standard. If we hit Control Enter on that line, it will create that model fit for us. Again, there's no missing values in the Cochrane Beets data set. Now I'll have to go back to my slides so I can remember what it is that, again, all these slides, and I have a full text version of the lesson. Those are all on the website, so you can go access those later on. Yeah, so this is the code that we're going to be running now. So we did the fit, and then we're going to try to make a plot of the observed versus fitted values to see if the model is a good fit to the data. We want like sort of a one-to-one relationship, ideally, between observed and fitted values. So we're going to say on the x-axis, we're going to plot the observed yield values. And on the y-axis, predict parentheses fit means we're going to plot the predicted values from the model that go along with those observations. Okay? That's what we're going to do. So I'll replace these blanks with predict parentheses fit. And the plot function will create a plot, Control Enter. So there's, you know, a more or less positive trend between observed and predicted values. Everything works fine. But here, I'm just going to artificially turn one of the y values, one of the yield values, into a missing value. I just randomly decided to take the third yield value and get rid of it and replace it with an NA value in the data. Obviously, this is not something you would do in practice very often, but this is just to illustrate what happens when we try to fit a model to an incomplete data set with missing values. So I'll hit Control Enter to run that line. And then fit 2, we're just going to fit that same mixed model again, but this time a missing value is in there. Okay. Now, some model fitting packages in R would actually give you an error at this point because of the missing value. Some would give you a warning. GLMN-TMB, it does give you, I believe, somewhere in its summary output, it will say there is a missing value in there, but it didn't give you any warning. Like, you wouldn't know just from running that code the difference between the two fits that we made, right? One has a missing value and one doesn't. It just silently deleted the observation with the missing value from the fit and just went with it. So what if we try to plot these observed yield values, and we try to predict fit 2 is what I call the second fit with missing values, and plot those, what will happen? We got an error. You can see it says error in XY coordinates, X and Y lengths differ because Cochrane Beats has 42 rows, but the predicted values only have 41 because a missing value, the missing value just gets eliminated from the model predictions, and so that's what we get. So you can check this. You can check this by looking at n row is a function that says how many rows are in a data frame, essentially a tabular object that holds data in R. We type n row and hit Control Enter. You see it has 42 rows. This says nothing about whether any of the rows have missing values in them or not. It just means there's 42 rows in the data. But we can use the function n_obs for number of observations on a fitted model object, which will tell how many rows were actually used to fit the model. And it should be 41 because there were 41 complete rows in the data that we use to fit the model. And that's why we get the mismatch. If you wanted to plot the observed versus fitted, you would have to write essentially some custom code to, but you would either want to delete the row from the data set before you fit the model, or create a special vector of predicted values that had a missing value in the same place where it was in the data. I won't go through that right now, but this is just to illustrate the pitfalls that can occur if you have missing values without accounting for them properly. And let me see, I believe I have some more slides to talk about this. Yeah, so the next thing we're going to talk about is visualizing missing data. And I just wanted to show you all a few kind of neat little packages that R has for producing some graphs and tables for showing missing data in a data frame. And there's two different packages we're going to look at. One is called Vim. I think it's visualization and imputation of missing data or something like that. And it uses syntax and plotting appearance that's similar to the default R plots. But if you like ggplot for your R plots, there's a package called NaniR. I'm not really sure why it's called that. It used to be called ggmissing, which to me made more sense. But then they included some other non-plotting functionality into it. So to illustrate that, changed its name, and it is kind of made more aligned with the tidyverse and ggplot packages. So if you like those type of plots, this is the library for you. Although they both make similar looking visualizations. And these are for a lot of the examples that I'm going to be talking about in the next little bit, we're going to use the same example. It's a very, very small and simple data set, just a little toy data set to illustrate to you what's going on. And this is a JACID or leafhopper abundance data set where I guess in a few places in India, the abundance of leafhoppers was measured, and then environmental covariates like temperature and humidity and things like that were taken. So we have 8 columns, one of which is our outcome variable, the leafhopper abundance, and the others are different weather variables. And the data set that I got was complete, but I just artificially deleted some values. So this is missing completely. This is not super realistic because they're just missing completely at random. And the deletion was independent for every covariate. Like I didn't say temperature and humidity are missing together. I just first said randomly take away some temperature values, then randomly take away some humidity values and so forth. So this is kind of like the simplest and least problematic kind of missing data you could have, but we're just getting started here, so I think it's good to start with something simple. And what we're going to do is we're going to import the data. If you're on your own machine, I've posted the data on a URL, but if you're on Scinet, you can just run the folder called data within the project contains the CSV file that we're going to import from, which you can just run that line if you're on Scinet, and then we're going to start to look at the data. So you can skip the line where it's importing from a URL and just read it in from its location in the data folder within our current working directory. So go to their line. It might not be line 100 anymore if you've typed in notes for yourself, but for me, it's still on line 100. Hit Control Enter. It will, now you can see in our workspace, there is a data frame called JASIDS that has 58 rows and 8 columns. And if you use the head function, that will print the first few rows of a data frame. Head, parentheses, JASIDS, Control Enter. So you can see that that all the variables in the data frame are numeric, floating point, and here and there's an NA or 2. I didn't put any missing values for the outcome. The leafhopper abundance has no missing values in it, the JASIDS column, but some of the covariates do. So yeah, for whatever reason, let's say it was not possible to obtain a maximum temperature reading that goes along with this observation of leafhopper abundance. So it's NA there.
I can't open the file in my local folder here. Is that was some permissions or?
That
Line.
is everyone on Teams following along? If anyone needs help, please let us know. Okay, got some thumbs up. Excellent.
Okay.
Thank you, Grant. It really is nice to have a helper. It's hard to like run around the room and help people while you're trying to talk with the front. So I'm really glad he came with me here. Let's start by using a very common function in R for looking at the contents of an object, which is summary. Summary is a function that can be used on all kinds of objects in R, such as statistical model outputs and things like that, but it also works on data frames. If you call summary on a data frame, it'll give you summary information on each column, one of which is the number of missing values in each column. And so let's do that. Here we can type summary parentheses, summary parentheses JASIDS, and hit Control Enter. Again, you can hit Escape or click to dismiss the autocomplete. And here in the console, you can see that for each column, you get summary statistics like minimum, mean, and quantiles and things like that. But it also, if there are any missing values in the column, you get this NAs 9. If there's no missing values, nothing will show up there, but it will tell you how many missing values there are in each column. And so remember, we have 58 rows, so some columns have as many as 12 missing values and some have none. And there's also a function called glimpse, which is in the dplyr tidyverse package. I can hit Control Enter there. And it shows you the first values in each column of the data. It doesn't total up the missing values, but if there is a missing value in certain versions of RStudio, the NAs will be highlighted in a different color, but for whatever reason in this color scheme, it doesn't show up that way. But depending on your version, if you're doing it locally, you might see them highlighted. Another function that's very useful for looking at missing data in our data frames is complete.cases. And complete cases, if you call complete cases on the data frame, it will return a vector with the same number of elements as the data frame has rows. It will be true if that row is complete, if it has no missing values. It will be false if there's any missing values at all in that row. And then we can call table on the output of complete cases, which will say how many trues and how many falses there are. The trues mean how many rows don't have missing values. It escaped there. And the false is how many rows have any missing values in them. We'll hit Control Enter there. So 25 of the 58 rows have at least one missing value in them. So that can be useful, useful to when you're exploring a data frame. And we can also use a function called is.na, which will, you call that is.na is called on a single vector of values, and it will return true if the value is an NA, is missing, and it will return false if the value is not missing. Now let me just, I can't remember what I put in the slides for this, again, since I haven't taught this lesson before. Yeah, and then you can, what I often do is I put an exclamation point before the is.na. An exclamation point is a negation operator. It will turn the trues to falses and vice versa, because I think it makes more sense to say true is good and false is bad. True means it's not missing. False means it is missing. So I usually do not. You can read the exclamation point like not. So not is NA. And then you can call that on a specific column of the data frame. Like let's say we wanted to know how many missing temp max values there are. We can make a table of the not is NA of that temp max column. So let's try that. So here I'll put an exclamation point, not is dot NA. And then the $ operator is used to pull out an individual column from a data frame. And the column that we're looking at is called temp underscore max. So this will create a table, true for any case where temperature is present, false for any case where temperature, maximum temperature is missing. So here we have 12 missing and 46 not missing. And you can make 2x2 tables or more if you want to look at where two variables are missing together or separately. And I'll show you how to do that. We'll use the with function so that we don't have to repeat the name JASIDS multiple times. So it says within the JASIDS object, let's make a two-way table of the missingness of maximum temperature and minimum temperature. The way we do that is we'll call the table function. And again, we'll want to do the not, so exclamation point, not is dot NA for temperature maximum, and then a comma, and then do the same for temperature minimum. Exclamation point is dot NA. So I'm starting to kind of speed things up, so please let me know if I'm going too fast, and I will wait for a minute to let everyone get caught up. And again, you could, if you fall behind, you can copy from the filled in blanks worksheet. Plus, a lot of this code doesn't really build on itself too much. If you miss a line of code, for the most part, it will not affect forthcoming lines, because later it will, but here we're just looking at individual examples. So if I hit Control Enter and execute this line, I can see that there are no rows where it's both false. So there's no rows that are missing both minimum and maximum temperature. There's 12 rows that are missing only maximum, 2 rows, because that's the one that the first of the two is the one across the top. Then the second one The one that goes down the columns is the missing minimum temperature. 2 rows are missing only minimum temperature, and 44 are present for both. And again, if you get stuck here, I'll just open this in the background. Yeah, if you go back to the Files tab and go to the MS 2026 directory and open worksheets filled in, you can open up the missing data worksheet with everything filled in. And all the code is here, filled in already. Like what we're doing right now, there it is. So it's all filled in, but I'm going to continue to work off the one with blanks filled in so that you can see how to type stuff in. But I just want to point out once again, if anyone missed it, that if you fall behind, you can start to fill in the blanks. Or you copy the code with the blanks already filled in. Okay. Slides here. The first missing data visualization that I wanted to show you comes from the package called Vim. And there's kind of a handy way to summarize missing value patterns in a data set and make a little plot. You know, you probably wouldn't put this plot in a manuscript, but it can be useful for yourself for exploring data. And the way that the Vim, I'm not going to go into too much how the package exactly works. But there's this function called AGGR, which I guess stands for aggregate, and it, for each variable and for each pairwise combination of 2 variables by default, it will compute the number of missing values there, and then you can call plot on that to make a visualization. And I've also included this argument numbers equals true. You don't have to by default, but it will give numerical summaries of the proportion of missing values in the different combinations by variable. So let's try it. So we're going to plot the AGGR. So we're going to call aggregate on JASIDs, and then we're going to plot that with numbers equals true. Hit Control Enter. And not enough horizontal spaces, but that may be because I'm on a small window in the browser. Let me try that again with more space. There we go. So yeah, this is what comes up from the numbers equals true. First of all, it just makes a little bar graph of what percent or what proportion of the values in each column are missing. And it also, for each pairwise combination of variables, it shows which ones have any missing values in them and what proportion. These columns should be labeled as well. Let me zoom in on the output. Yeah, you may see something different if you look at it on your own, but this would be like the RF column, and then this would be the JASIDs column. So it's like what proportion of the data have RF and JASIDs, some missing values for both of those, or for one or more of them, I think. Can't remember exactly what this means, but this is like the overall frequency. So this is like how many have some missing values, and here would be 57% of the data have no missing values. Blue usually indicates data that are not missing, and red indicates missing. That's kind of like a common convention in visualizations of missing data, is to have blue be observations and red be missing, and I followed that in the customized plots that I've made as well. I also wanted to show from the non-ER package, there's a function called vismiss, VIS_MISS. which creates a table of missing data visualization by row for a data frame. And I'm not really sure why, but by default, when I didn't include this additional argument, it produced like a huge amount of space between the axis labels and the plot. I think it's a bug in the package, which I had to make a workaround for. Hopefully it'll be corrected in future versions, but BIS_miss, and then I've included this thing to get rid of the spacing between the axis labels and the actual plot. Hit Control Enter. And so here, basically, it this kind of like converts the entire data frame into a heat map and shows where the values are missing. So it's just row by row. Gray means it's there, and black means it's missing. So you can see, and then it also gives little little indications of what percent of the values are missing for any given column. So all in all, 7%. If you just tabled up all missing versus not missing, about 7% of the values are missing. But some columns have up to 20% missing, and some have 0. And there's other arguments you can use on viz miss, like cluster. You can resort, it'll automatically resort the rows so that you can see, instead of just, this is just the order that they appear in the data, but you can also sort it by whether it has missing values or not. So if you do cluster equals true, I'll hit Control Enter. There, you can see, yeah, for whatever reason, by default, it's giving this weird space in between the axis. I didn't include the fix for that on here, but what this does is it clusters together like rows in terms of missing values. So like some rows only have the relative humidity 2 missing, some have RF and maximum temperature missing, and so forth. So it just resorted the rows to cluster together the missing versus not missing. And if you do sort miss equals true instead of cluster equals true, so I'll hit Control Enter there. It just reorders the columns in case you wanted to look at the columns in order of most missing to least missing values. Just some options for visualization. Yes, so yeah, Brad, I don't know if you may have a different version of if you, maybe they did correct the bug in the package in a later version. So you see the big space too. Yeah, so it just depends on that.
Yeah, I was getting errors.
Yes, I see. Yeah, I didn't want to get too much into it, but yeah, again, if you really want to make one of these plots in a nice, way that would look good on a slide or something, you may need to tweak the appearance of it, but we can debug that later if needed. But these really aren't, again, for like presentation that much. I would say they're mainly for exploratory work, so it doesn't matter a lot if they don't look perfect. Okay, now let me see. Maybe this is, yeah, I think this is a good time to just take another 5-minute break in case anybody needs to stretch their legs or anything. So let's go ahead and do that. It's 10:27. We'll break till 10:32. You got plenty of time, so because we're at a good stopping point here. And anybody feel free to ask questions on Teams or whatever. I'll be here to answer them.
Can I share my screen?
Yeah, sure. Let me turn off my screen share temporarily, and then you can
We are.
see where are you.
I find
I'm good. That's.
Okay, yeah, you can go ahead and share your screen, and I'll try to help you out.
that's a,
That's okay. That's okay.
that's. Well.
You, I mean, you should say this person.
Can you
Says.
see?
Okay, well, I can see I can't see I can only see your desktop. I can't see I think you're sharing the wrong screen.
That's
Oh,
the way the top.
I can't see
Icon.
what you're trying to show me.
I think the most of them is. Face. What?
it's not letting me, I think. Okay, let me see this option.
Okay, I can see it now.
Ah,
Yeah, okay, you typed AGG, but it's AGGR. That's and numbers equals true. Yeah. AGGR parentheses. Oh, and yeah, there we go. And then numbers. Wait a minute. Wait, that's not right.
Oh,
That's not right. You added an extra parentheses.
remove it?
Yeah, get rid of that one. The close, just have the open parentheses, not the close. Well, yeah, I think you have you have it set on type over. You're gonna hit insert on your keyboard to get rid of the type over because you're yeah, hit insert on your keyboard. Press the insert button on your keyboard. There we go. Yes, so now, yeah, there we go. Now delete that. Or add AGGR open parentheses. Open parentheses, not quotes, parentheses. Not quotes, parentheses. Yep. JASIDS is the name of the data frame. And then it should be numbers with an S equals true. It might work without that, but better to put the complete name, but it should work without it.
Yes, I think it did work. Okay.
There we go. Yep, there you go. And there, you're gonna just want to type in DIS_miss is the name of the function that is used from the Nania package to plot DIS_MISS. V as in Victor, not E.
Underscore miss?
Yep, that's it.
Okay.
Yep. Now, if you run that line, it will make the missing data plot.
Okay. We are here or we went?
Yep, there you go. So it just popped up.
Okay.
Excellent.
Thank you.
You're welcome. So. Just a second and I'll get us started again. Okay, all right, I need to share my screen again, so we'll go back to the. Thing. Okay. So. Back to the slides. I'll just interpose from our exciting hands-on coding to give a little bit more background, and then we'll get back to some examples again. But I'm going to start telling you the different strategies that you can use when faced with missing data, and starting from the simplest, progressing to more complicated, and how you would implement each. We'll give a few examples in R of how you implement them. So what to do about missing data? I kind of classify strategies for dealing with missing data into three bins. One is various ways of just deleting the observations that contain missing data and working with what's left over. That's one way, like we did when we did NA.RM equals true, for example, when we were looking at the mean. That's just getting rid of them, not worrying about the process that underlies why they're missing, just say, we pretend they didn't exist ever. Which again, if it's completely at random, is fine, otherwise not so fine. Another way is imputation. Imputation is essentially coming up with an educated guess of what that missing value would have been if it wasn't missing. In the alternate reality where that data wasn't missing, what do we think it would have been? And you can do that in kind of, the simple way to do that is just to do your imputation and then proceed as if that imputed value isn't missing in his data and treat it the same as everything else. That can have problems, which we'll go into. The sort of most complicated, but probably the most robust and statistically defensible way of doing it is to use multiple imputation, which is imputing multiple possible values that missing value could have been, which then accounts for uncertainty. Since we didn't actually observe the value it was missing, it could truly be multiple actual values. So then if we do multiple imputation, we can actually account for that uncertainty in our final results.
So you're doing like a distribution
That's right. And
for
we,
each missing point?
exactly. Very good. Yes. Very astute. And that is exactly what we're going to do, but we're going to start simple. And that's the last thing we're going to do today is look at the distribution for each missing value. So what strategy do we choose and why? The most consequential factor of what strategy to choose is how much missing data we actually have. If only a handful of values are missing out of a large data set, it may not really matter to choose a very sophisticated and fancy and formal means of imputation. It's not going to affect the conclusions that much, so you could just do a simple method. And the more missing data you have, the more impact any biases from the missingness is going to have in your conclusions. So the more motivation you should have to formally account for that. Now, some people say, well, how much has to be missing for it to matter? I don't want to throw out any numbers because there's no hard and fast rule. It really depends. Like even if there's a strong bias, if even a couple of values are missing, it can strongly affect your conclusions. So I'm not going to say like it's less than 5% missing or 10% or whatever. There's no rule. And another point I want to make is if too many values are missing, again, there's no hard and fast rule for this, but if, a huge proportion of your data are missing, there's also not much point in kind of doing some complicated method because then, you have to have some information there to make those missing data models. And if too much is missing, you're not going to have a good missing data model, and no fancy stats are going to save you. Your results are just going to be very uncertain anyway. So imputation is kind of for that sweet spot where there's like enough missing to matter, but not so much that you can't make the imputation model. Yeah, but there's no rule for exactly, it depends on your data set. Hopefully that makes sense and I'm not just sounding wishy-washy there. So another thing, we've already talked about this a couple times, but the way in which the data are missing determines your strategy as well. Because if your data are missing completely at random, then basically observations are just missing are deleted at random from the data set. There's no bias, it's just that it reduces your sample size. But if the data are not missing completely at random, that means that bias is introduced unless you account for it properly with imputation. And again, the severity of the bias depends on the degree of non-randomness and on how much is missing. So this brings me to what we're going to do. The first simplest strategy, which works best if you have missing completely at random, is to just, if there's any missing values in an observation, in other words, in a pair of outcome and predictor variables, If it has any missing values, you could just get rid of that whole observation. And you would basically delete observations that contain missing data until you end up with a complete data set with no missing values. There's two main ways to do it. One is called list-wise deletion. Some people call that complete case analysis. That means basically deleting rows from the data, like individuals or subjects from the data that have any missing values, and only taking the complete cases. And we'll also mention pairwise deletion and give an example of that too. And so I would say across all scientific fields, list-wise deletion or complete case analysis is the most common way that people deal with missing data. Many scientists go their whole lives without formally making an imputation model for missing data, although they should. Many of them kind of get away without it. Most data that we're going to be using for statistical analysis software like R and SAS, some people in R call it tidy data. Each row of your data represents a case. The columns are variables that would go into a statistical model, and the rows are observations or cases. What if we wanted to take a data frame that has missing values and delete any rows that have missing values in them, resulting in a complete data set? You can use the filter function from the dplyr package to do this. If we say we're going to create a new object called JASIDS complete only, and we're going to filter by complete cases, and in dplyr, the dot means the current object. So filter means keep only the rows where this is true, complete cases of the current data. So it's going to take that data frame and give us a new one that only contains the rows from the original data frame that don't have any missing values in them. Can do that.
So
Yes, okay.
this is an R coding thing, but just, does it just assume that you want to operate on the most recent variable you use, like you?
That's right. So this pipe operator means take the output of this line and pass it in as the first argument to the next line. So we're going to say filter
Oh, that's the pipe.
the
Okay.
JASIDS data, keeping the rows where the current object is complete in those rows.
Gotcha.
Yes. Thank you. Great question. Yes, a lot of operators in R have percent, something percent, like matrix multiplication in R is percent, asterisk percent, and things like that. So it's just a common,
But several of us use MATLAB
Yeah.
a lot, and MATLAB, that's the comment operator, so that's
Yes.
why I was like,
Yeah.
well, that's commented out.
exactly. So yeah, it's like you have to shift your brain around or whatever, because R uses the pound or hashtag, as the young kids call it, for comments. So yeah, filter is the function that selects rows to keep. And then complete dot cases, which we've already met before. That's going to keep. So I'm not modifying the JASIDS data frame. I'm assigning the results of this to a new object called JASIDS complete only, because we don't want to. We want to still have access to those missing rows in the future. So we're making a new object. So I'll hit Control Enter. Okay, here's JASIDS complete only. Now, as you can see, JASIDS has 58 rows and the complete only has 33. Those are the complete rows. Now, this, by way of illustration, I want to show you that we already showed this with the glmntmb package, but also in base R, the LM function, which is just to fit a simple linear regression, will do this complete case analysis for you, even if you don't explicitly tell it to do so. For example, if we just pass the JASIDS data in as the data argument to the linear model function, we just want to fit a model trying to predict leafhopper abundance as a function of maximum temperature. I'm calling that model 1. And then also, let's say we also wanted to do it as a function of maximum temperature and wind velocity for whatever reason. I'll call that model 2. This is just for illustration. So I'm just going to hit Control Enter to run that line. Hit one linear model. Control Enter to hit a second linear model. And then if you remember the NOBS function tells us how many rows or observations were used to fit the model. And obs model 1 is 46. Those are how many rows were used to fit that first model, and model 2 is 41. So LM will only do the complete cases for the actual variables that you use in that model. It doesn't have to go all the way down to just 33 observations, because there are some rows in the data. While they do have some missing values, they still have JACIDs and temp max present. So it will use all those. So it depending on what variables you put in as predictors and outcome, different numbers of rows may be used to actually fit the model depending on where the missing values are at. Which is both good and bad, because in a way, it's not great if things are happening behind the scenes that you don't have full knowledge and control over. So it's good to always check these things. And another type of deletion, so that's list-wise deletion. We've deleted rows that are not used. Another one is called pairwise deletion, where that's called available case analysis. So instead of using complete cases for everything, for each separate calculation, we take the rows that we can use for that. So like, what the most common time where that comes up in R is a correlation matrix. Like, let's say we wanted to make a pairwise matrix with the correlation coefficient of every pair of variables in the JACIDS data set. We could we could do it either of two ways. We could either first do complete case deletion and keep only those 33 rows that have no missing values, then do correlations on that. Or we could, for each pair of variables, we could take the non-missing values from them, but there might be different numbers of observations used to get the correlation in each case. And I'll show you how to specify which method we want to use if you're trying to make a correlation matrix in R. Let's see. So trying to like look at two screens at once here. By default, the core function COR is one that is used to make a pairwise correlation matrix. If you just specify that straight up with no, hit escape there, with no additional arguments, just like with mean and median and everything like that, it will produce NA if there's even a single missing value in any of the rows that in that pair of variables. It will be NA by default. So with core, you don't just put NA.rm equals true. You actually have to specify which type of, if you want to use listwise or pairwise deletion, there's a different argument for that for each one. The argument is called use. And it's going to be in quotes, a character string. If we say use equals complete dot obs for complete observations, it will just take that 33 rows that are complete and do the correlations there. So we hit Control Enter. You can see now we don't have any missing values in our correlation matrix because it's deleted any rows that have missing values and made the correlation matrix. We could also do pairwise dot complete obs. Pairwise dot complete dot OBS. Kind of a mouthful. That's going to use in each case a possibly different number of observations. So again, there's no missing values there, but if you look if you look closely, they are not the same output in each case because different inputs was used. Yes, William.
So I got a error when I ran the second, the line on 134. saying that it doesn't recognize the use argument.
Could be a typo.
That's what it was.
Okay.
Okay.
Yeah, so yeah, this is, I think you can actually, you might be able to like type an incomplete version of this. If you just say use equals pairwise, it should still work. Let me see if it does. Yeah, as long as it is, you can partially type in that argument, it'll still work. But the full thing is called pairwise.complete.hubs.
So then, if we were to select the JASID's complete data frame instead of JASID's, that would have given us the same results as the complete hubs.
Correct.
Because we previously.
Correct. You've done list-wise deletion. Yep. Okay. Grant.
I've used the pairwise before to estimate a covariance matrix, and you can wind up with some like pathological things that happen. Like,
Right, because totally
yeah.
different, yeah, so you're using the most data possible for each one, but it could be using very different subsets of the data, so. Yeah, great point, I mean, it's something to be aware of, and you have to go into it with your eyes open and know exactly what you're doing.
So you wouldn't want to just do that for convenience because it has really could have very unexpected results.
It
yeah,
could,
like
exactly.
That kind of situation happened where you have two variables that are correlated with one variable, but neither of them are correlated with each other because of which subsets were used. So,
Yep, yeah, and if you did a formal imputation before you did the correlation matrix, you might be able to recover the true relationships. So let's go into, that is a wonderful segue into, yes, I'll skip over these. Yeah. Let's see. Yeah, I'll just kind of skip these notes right now. You can read the full text version of the lesson just, so that we can get to the more exciting, stuff here, which is, okay, we've seen now some various ways we can delete or ignore the missing data, but what if we actually wanted to impute missing values? So list-wise deletion can actually waste a lot of data. Like if you had hundreds, like let's say you had a microbiome data set or something that had thousands of taxa or, any kind of omics data set, right, would have many, many, many variables. And, an observation could have 99% of them be there and a 1% missing, but all the observations could have one or two missing values or most of them. So if you just kept only complete rows, you might delete almost all your data. So, and of course, if data are missing not completely at random, you're going to get biases from just ignoring the missingness and pretending it wasn't there. So what can we do? Well, we're going to, from now on, for the rest of today, we're going to be looking at how to impute values in our data set. And by impute, I mean substitute missing values with another value of some sort, using other information that we have to basically guess or make a probabilistic inference about what that value would have been if it could have been measured. Sound good? Okay, let's go for it. So we're going to start simple again and work our way to more complex cases. Kind of the simplest way to deal with missing data would be to impute using the mean. So like for every missing, for example, if temperature is missing from our data, we're going to replace every missing temperature value with the mean of the non-missing temperature values. That is a very common way to deal with it. Or if it's a categorical variable, you could use the mode or the most common category to instead of the mean. Then we'll start to get more complicated. Like if you have data that have space and time structure, you could pull adjacent observations. Like if you had temperature for, hourly temperature values, but 10 o'clock is missing, you could take the average of 9 and 11 o'clock, and that's a reasonable guess for what the 10 o'clock temperature might have been. You can also take randomly selected, instead of taking the mean, you can take a randomly selected value from another observation that's not missing. Those are all kind of simpler ways, and then there's also ways that are based on regression models that we're gonna get into. Those are different strategies. So we're gonna start simple. Replacing missing values with the mean of the non-missing values. Now, again, if the data are missing completely at random, this will not introduce bias. It will give us the same conclusion as if we didn't do this. So if they're missing, again, if it's missing completely at random, this is okay. And there's a function in base R called replace that we're going to use to do this. And just the rest of this is just technical about how the replace function works. Replace has 3 arguments. First, input is the vector that contains missing values. The second argument is the locations in that vector that we want to replace. So first argument would be X. Second argument is .na of X, means at the locations in X where there is a missing value, we're going to replace it with something. The third argument is what we're replacing it with. And I've created this custom function called impute mean that takes a vector X and will replace everything in X where it's missing with the mean of the non-missing elements. Mean of X, na.rn equals true. And you could do the same for the median. I've also defined a function called impute median, which, you know, if you wanted to use the median instead of the mean, the only difference there is that I've replaced mean with median. So let's define those functions ourselves as well in your own environment. So it's going to use the replace function. X is the first argument. Second argument is dot and a. Where are we going to replace? The places where it's missing. What are we going to replace it with? The mean of X. But again, we always have to supply na.rn equals true to get the mean of the non-missing components of X. Rn. Okay, escape to dismiss that autocomplete and then hit Control Enter. And again, I'm just defining a function right now. It doesn't produce any output. It's defining a function to use later. And the second one, just like that, except it's identical, except that instead of mean, you could also use median. Okay. And now, what if we wanted to create an imputed version of the JASIDS data set where every missing value is replaced by the mean of the non-missing elements in that column? We can use this type operator again. And again, I'm not going to modify JASIDS in place. I'm going to keep the original one with missing values. That's usually a good practice so that you can refer back to it later and compare it to the missing one, or the one where it's been imputed. I'm going to create one called JASIDS _ mean _ imputed. And the way that you would apply a function to all numeric columns of a data frame using tidyverse is mutate, which means modify columns. And then we're going to use across, which means apply this function to a number of columns. The first argument of across is which columns do we apply the function to? And that's where parentheses is dot numeric. And the second argument is what function are we applying to those columns? So again, we're going to say, okay, for every column, look at it and see if it's a numerical value, not character. If it is, use this mean imputation function to replace the missing values with the mean of that column. Again, all the columns in JASIDS are numeric, so it's applying it to every column, but this is, in the general case, you might have some data that are not numeric in your data frame, so this is how you would apply it only to the numeric columns. So I'll hit Control Enter here. And then this is, just so you can see, I've made these, customized functions to plot imputation results. So I'll run that real quick and then I'll go over what it looks like so that you can understand how these outputs are going to look moving forward. So first we're going to make a histogram. And I'm just going to use the temperature maximum column. And in all the histograms I've made, the solid blue is the distribution of the non-missing temperature values, and the hollow red bars are the distribution of the imputed values. Now you can see that there's only one bar in the imputed ones because we've imputed all the missing temperatures with the same value, which is somewhere around 30, which is just the average of the non-missing temperature values. And you can also, I also made a function that will plot the imputation performance using two variables against each other as a scatter plot. Control Enter there, you can see it. And you don't have to run this on your own. You can just look at this, but if you want, you can run it. And you can see here are the values that are been imputed for minimum and maximum temperature. And you can see that like this is minimum temperature. And so anywhere where maximum temperature was imputed, again, it's just all the same, 30-ish, and minimum temperature was around 20. So there, that's what it looks like. So, you know, this is not something I would recommend doing if you have a lot of missing values and are concerned about biases. This is kind of a quick and easy way to impute a very, very small number of missing values. So we're going to go another level and try to look at adjacent observations in space and time. If you have a time series data and a value is missing, for example, we can use the values on either side of the missing value to fill in the one that's missing. I'm not going to get into the spatial. Yeah, question.
So why isn't it a constant, the red circles that are replaced in that data set? How come it's not a constant? There's two.
Yes,
two
because these ones are the ones that are along this line are the ones where temperature minimum was observed, but temperature maximum was not observed. So we have variation in temperature minimum, but all the same temperature maximum. And then there were some where temperature maximum was observed, but temperature minimum was not. And those are those ones.
Oh,
If they were both missing, they would all be right on top of each other, right where those two things would meet. But there, I guess there weren't any rows that have both minimum and maximum missing. So it's the mean of each of the respective ones. Okay, so I'm not going to get into the spatial imputation in this lesson because that's where you get into things like Kriging and stuff like that, which is a little bit too much to go through in this intro lesson. I'm just going to do some very simple methods for imputing missing values in a time series, but this is only scratching the surface of that as well. There are very complicated methods for this, but again, this lesson is just to give you the very basics and kind of expose you to what's out there that you can then use as a springboard to learn more in the future. So we're just going to do very simple stuff with this. Now, the JASIDS data is not a time series data, so I'm going to use a different example data set for time series data, which you're going to have to read in. It is, if you ever did one of my mixed model lessons, we've used this cow tuberculosis data set before, but I've made a new version of it with some missing values in it. Basically, it's an experiment where they gave some cows tuberculosis and some not, and they gave some type of iron supplementation and some not, and then they measured the weight of the cows at a bunch of different time points, so you could look at the rate of weight gain and the different treatments. Doesn't really matter exactly for our purposes what it was, but that's the basic layout of the data set. If you're on your own local computer, you can read it, import the data from a URL. It's called Diggle because it comes from a paper by Diggle et al., but I've just called it data frame cows. Yeah, so go to line 155 and just run that line. It will import the data from the folder called data. You can see there's a data frame with around 600 rows and five columns. I didn't put this in the worksheet, but if you just type in your console, head, parentheses, cows. And we'll look at the first 10 rows. Yes, so you can see that there's different IDs for the cows. Individual cows have IDs. There's columns indicating what treatment it belongs to, and there's time points. And the only one that has any missing values is the weight. I've just, again, completely at random, gotten rid of some missing values or gotten rid of some of the weight values so that imagining that for whatever reason, cow A1 was skipped its weight measurement on a particular day. So the first thing we're going to do is, this is just a, sorry. We just need to convert some of the columns to factor variables for fitting statistical models later. And this is, so again, across means which columns we're going to modify. The second argument is what function we're going to use to modify them. The function is factor. Escape. That's just going to tell R that those columns are a special data type called factor, which is usually used for treatments with specific levels in an experiment. I'll run that. Okay, now what is one way we could impute the values in a time series? Well, a simple way that maybe isn't the best, but we could use as a very first try is called last observation carried forward. Like in Excel, if you just fill in missing values with whatever the value was, like before the last one we observed before it was missing, we can we'll just fill those in. So like there's a tidyverse package called tidyr that uses the fill function for this. There's also a function in the package called zoo, which is used for time series, that I'm going to use that function to do this imputation. So basically what we're going to do is within each animal, we are going to, if there's any missing values, we're just going to take whatever its last observed non-missing value was and fill it in. Okay? And so how are we going to do that? We're going to use a pipe for this. We're going to start with the cow's data frame. First, we're going to group by animal because we don't want to accidentally fill in values from a different cow. So we're going to make sure that the operations that we're going to do are grouped and only done within each animal. The column indicating the cow's ID is called animal. Okay. Then we're going to use the arrange function. That will sort the data first by cow, by animal, and then by day, just to make sure the data may already be sorted in this way, but this will just make sure that first the data are sorted by animal and then in increasing order by day within each animal. Arrange, so if it says animal, comma, day, it will first sort by animal ID, then by day. And then I'm going to make a new column. I'm going to call it weight LOCF for last observation carried forward imputed. And the function that we're going to use is NA.LOCF. So for NAs, we will fill it in with last observation carried forward. That's in the zoo package, which is like a time series package. we're gonna use the weight column. But we're actually gonna use NA.RM equals false. And what that indicates here is, for whatever reason, the NA LOCF by default, if it has any missing values at the beginning, if the first observation for a cow is missing, by default, it will just remove those values and give you something with a different length than you started with. I don't understand why that's the default, but we don't want that. We want to just, if a cow's first observation was missing, we want to leave that missing value there for now. So we're going to say NA.RM equals false. Okay. And hit Control Enter. Oh, and again, I've made a new data frame called cows imputed for this, so that the original one is still there. And now, basically what this did is it filled in the blanks with whatever was last observed before, and with a new column. We can compare side by side the one with missing values and the one with imputed values. But some of the cows might still have missing values in there because their values on day 0 or whatever the first day was might be missing. So there, we're just going to impute backwards and take the first non-missing observation and go backwards in time with that. And so basically the way we're going to do that is just we're going to modify this imputed column and impute it some more with the mutate function. Again, we're going to use NA.LOCF. Again, with NA.RM equals false, but we're going to use another argument called from last. FROM capital LAST equals true. Capital TRUE. And that will fill in backwards if needed. Control Enter. Now, I didn't put this in the worksheet, but if you look at the head of cows underscore imputed, I use tab completion to complete that, comma 10. You can see here's the original weight column still has NAs, but the imputed one has filled them in with the previously observed value. And if the first day was missing, it would fill in that as well with the first non-missing value. And see, since we had 2 in a row, it actually filled in multiple days with the 160 because there were 2 missing in a row. Now, that may not be the best for this data frame because the cows are gaining weight the whole time, right? And so like its weight kind of went up by a few pounds every day, and then there's a gap here, so like it's 160 going up by 40 to 200. Obviously, doesn't make a lot of sense necessarily to say it was 160 the whole time. So the next most simple way to do this is linear interpolation, which is basically here. Let me see. I think I have it on the slides. I've got an illustration of that. Yes, so we've done all of that. Yeah, so this is how linear interpolation would work. Like it's the simplest way of imputing time series data using adjacent values, right? We can just making the assumption that the weight gain is linear, which it may not be, but making that assumption, we'll just draw a straight line between the non-missing points on either side and then find the using the equation for the slope and intercept of that line, find the y coordinate corresponding to the x coordinate where weight is missing, right? So like cow A4 weighed 290 kilograms on day 380 and 310 kilograms on day 478, but its weight on day 445 was missing. We can basically plug in these 4 numbers into the equation to get the slope and intercept of a line that connects 2 points and solve it for x equals 445, and that will give you the y coordinate here, right? Assuming that it followed a constant rate between those 2 dates. And here's first I'll show you this longhand, but there's actually built-in functions that do this, but just to illustrate, this is the formula. If you have your, x0 and y0 is the one before, and x1, y1 is the one after, and x is the time point at which the data is missing. This is the formula for calculating the interpolated value. And I've defined my own function to do this and then plugged in those numbers that I just mentioned. If like the first, on day 380, this is its weight. On day 478, this is its weight. What would its weight be on day 445 if, if it was linear in between? And so if we run line 170 to define the interpolation function that I just made, and then we're going to run it with those arguments. So I called it interp or interpolate. And then the arguments all have names, right? So there's x, that's the coordinate that we want to know the y value for. X0 is the first time point. X coordinates of the first day. Y0 is the weight on the first day before the missing value, and then X1 and Y1 for the later time point. If we enter that in and then run that, you can see that it's around 303, which is kind of in between the two non-missing values of 290 and 310. Sound good? But you don't actually have to memorize that formula and code it in from scratch every time you want to use it, because there's a function called approx, APPROX in R that implements this exact formula that I just showed you. And I'll show you how to do that here. So again, we're going to group this so that the interpolation is done within each animal. We're going to make sure it's arranged within each cow in increasing order of time. And the function we're going to use, we're going to make another column. We had a weight LOCF imputed. Now we're going to do weight interpolation imputed. Approx is the function. The X variable is the name of the column in the data, which is day. The Y variable is the name of the column weight in the data. The next argument is X out, and that is which values of X are we going to produce interpolations for, and that will be day. We're going to produce interpolations for every value, even the non-missing ones, because if it's not missing, it's going to give us our same value back. And if it is missing, it's going to give us an interpolated value. And lastly, you have to use this this function rule equals 2, which means what does rule equals 2 mean? If there's an NA value at the beginning or end, there won't be a value on either side of it to impute with. We're just going to use the last observation carried forward or backward method in those cases. That's what rule equals 2 indicates. If you look at the help documentation for the approx function, I didn't just, I wasn't born knowing that. I had to look it up in the help documentation. And then
when you hover over the,
yes, you can look at the help for the function. If you hit tab while you're typing it, or if you hover over it, that's right. Where's my mouse here? Yeah. Yeah, it should. Oh, there you go. Yeah. There's the different arguments. And if you go, if you type question mark approx in your console and hit enter, it will pull up the documentation in the help tab. And it'll say what rule means. Using, if it is 2, the value at the closest data extreme is used. If rule equals 1, it will keep it as NA, which you might want in some cases. And then we have to put this $y because a prox returns a data frame with multiple columns, but we just want the imputed weight column, which is called y. That's why that has $y at the end. Hit Control Enter. Okay, and in a minute, I will show output of how all these imputation methods performed. I'm gonna do one more. And then after that, we'll take a short break. But we'll do one more here real quick. I'll go back to the slides for a minute. Just to give you some exciting historical background on this. This last kind of imputation is imputing missing values using randomly selected values from elsewhere in the data set. And this is known as hot deck imputation because back in the day, data was stored on punch cards and they were kept in stacks called decks. And the hot deck was the deck that's in the machine right now. So that's like the data set we're using. It's hot because it's in the machine. So like we're randomly selecting data from the deck we're using right now. So people still call it hot deck imputation, you know, referring to something that no one actually even, I've never even seen one of these machines in operation before, but they still call it that. So yeah, basically the simplest form of hot deck imputation is if you have a missing value, pull a random value from anywhere else in the data set and use that. Or you could stratify it. You know, for example, if you had males and females in the data set and one of the males had a missing value, could randomly select its value from only other males or whatever. You know, you could stratify the random sampling that way. And let's note one thing. Now, this is the first imputation method that we've seen that incorporates randomness in some way. Every one we've done so far has been, is going to give you the same result every time you do it, right? If you're imputing with the mean, it's always the same. This one, you could run a hot deck imputation multiple times and get different results. So it is actually the first one we've seen that does that, and that's actually our first foray into some uncertainty in the imputation. And we'll, yes, we still have plenty of time. I'm glad we seem to be right on time, so we'll be able to look at that in more detail soon. So how are we going to do that in Power? Again, we're going to use our group by, and this time we're not going to group by animal. We're going to group by the treatment combination and time. So like if this is, so we're going to do stratified random sampling to say if a cow in a certain treatment group of iron supplementation and a certain infection treatment group, one of the 4 combinations on a particular day is missing, we are going to replace its weight value with a randomly selected value from another animal from that same day in the same treatment group. And we're going to use the mutate. We're going to use the mutate to modify, to create a new column by modifying an existing column. We're going to make yet another imputed column called weight hot deck imputed. And we're going to use if else, which the first argument is basically if weight is missing, if is.na of weight. So the first argument of if else is going to give us a true or false. The second argument is what do we do if that's true? The third argument is what do we do if that's false? So first argument is weight missing or not? If that's true, we're going to sample from the non-missing values in that same treatment group in the same day. And we're going to do a sample with replacement. We might sample the same one multiple times. And if it's not missing, the third argument, we're going to replace it with just the value that's actually observed. So this is going to give us a new column that's going to contain the observed values of weight, and it's going to replace the missing ones with randomly sampled values from the same treatment group on the same day. So let's type that in. Right, so again, first argument is is it missing or not? So that's is.NA parentheses weight. Second argument is what do we do if that's true? We're going to sample, which means take a random sample from NA.omit of weight, which means the weight with missing values omitted for that particular treatment combination. The size is going to be a sample of the same size as the original, so size equals length parentheses weight. Length meaning the number of elements in the vector. And replace equals true. Sampling with replacement because we may sample the same one twice for multiple missing observations. And the third argument is just weight, meaning if it's not missing, we'll just keep it as is. Hit Control Enter. So yeah. Oh, I'm sorry. I should have done this first. I didn't run set.c equals 1, which initializes the random number generation at a pre-specified seed, so that if you run this on your machine and I run on my machine, we'll get the same result. So let me just yeah, I'll go ahead and run set seed equals set seed parentheses 1 first. So yeah, you want to do this before you do the sampling, then we'll all get the same results, which is, you know, if you want to reproduce the same random imputation again, you have to make sure you set a random seed before you do it. So I'll run line 180, then I'll run line 182 through the next few, Control Enter both times. Okay, now, before we take our break, the last thing I just want to show you is how these different imputation methods performed. And so these lines, I didn't make you fill in the blanks. You don't have to run them on your own computer if you don't want to, but it's just going to produce a bunch of plots. First, we're going to look at how did the last observation carried forward do. So here's a distribution. You can see there's not that many missing values in the data set. So this is what the distribution of the non-missing weight values looks like. And there's a distribution of the ones we imputed, the hollow red ones. And how does it look if we do a scatter plot? Yes, there are, yeah, there's a lot of data in here, so it's not immediately obvious what the, how these different values are, but you can see there's like some weirdness going on, right? Because like for the very early ones, it's kind of overestimating the imputed values are all bigger than the ones because it took values from a later day. So it's actually higher than the non-missing values. What if we did the linear interpolation? Hopefully that will look a little better in terms of that. Here are the distributions. Again, kind of hard to tell any difference there, but what if we look at the scatter plot? So yeah, we still get that problem because it didn't have anything to interpolate on day 1. So it is still pulling from later days to get that imputed value. But what about the hot deck imputation? On that line, again, don't really see a huge difference visually. But yeah, here you can see that the hot deck imputation is pulling from that same day. So it, at least for day, whatever the first day is, your imputed values have a similar distribution to the non-imputed, which might be what you want. So yeah, we've been going through stuff for a while. Let's we still have an hour, which is great. So we should be able to get through everything, but let's take a 10-minute break, you know, so that people can gather their wits again. So let's reconvene at 11:38.
We're about to fit a function to the data and replace it with the fitted function.
Yes, now we're going to start using other information from other columns of the data set to impute. Yep. Yeah,
I have a question that's completely irrelevant to the action.
yeah, go for it.
So much of it. Aesthetically, I really. The code, it breaks the line and not actually breaking the line.
Oh, yes, that's right. I probably, let's see, it should be in one of these, in edit. Where's the
Code.
No, code, yeah, code, soft route long lines. Take that away, it'll make the lines go out there longer. Yep. So, yeah. Not good practice to make the lines need that, but yeah, so that, you just have to check that option. Yep,
Line, gotcha. You get like that.
yep, sorry, I should have, said that before. Thanks for, asking that.
Oh, yeah, absolutely.
That's investigation.
Yes.
But yeah. So the drawings, very. Coaching.
Yeah.
I didn't make it.
It's extra work. You have a child now. You don't have time for that.
They need to. And we farm.
No, they're.
Still learning how to, live with a child. You're still learning.
Just said he threw it again. He used to make his own yogurt. Like, yeah, I know why you don't make your own yogurt.
That's stuff that I used to do, so.
Then we used to make some coffee names.
Well,
I got lazy on that. Maybe I got a raise or two and was just like, you know what? Exploradora does it so much better than what I can do. I got landed
to remember.
I got landed on the Exploradora. So
back then we didn't have.
I still have
Some coffee?
gift certificate.
Yes.
Oh, yeah, what's that?
Back then, we didn't have that many roasters, I think.
No, we did not. Like now it's 10-year-olds. Well, I even got like Exploradora, like I even got to see them roasting the machine they had, like 30-minute break from it.
We're just on the break right now.
Then we're gonna finish in 12:30. That's touching.
Man, I just saw these big old hogs out there.
Did y'all learn anything?
Double blade with.
You already know.
With your right saw?
No, with the 20 years, 22. The last.
I was like, it's not, it's bigger than a 250.
I'll talk to 250. I think I got cleaned out up there right enough here for you to see.
Good. That's fine. I was waiting for that a long time. You gotta inch it up and look at it, go out. People come back to mine. Boy, they drive like 60.
Y'all won't be able to go either. Oh. Maybe it is.
This meeting still going on.
Yeah, I assume so. Amanda, is there haven't come back? Hey, Jake.
Hello. Darren told me I think.
Yeah, they're really making them suffer in that meeting, huh?
Whatever the change is, crap to you.
What's that?
What quality is it?
They had a meeting with the national program leader for an hour and a half. No, it's not stopping. So,
That's random.
yeah, or
Is it still going on?
they maybe just decided that they missed too much and or whatever. Didn't they know you were here? Yeah, really. I mean, come on.
So if I look up Oregon, 6 feet.
I think I kept 12 feet in the conversation. I gave, I don't know what they call it, a phone that I had, in my office. No, I mean, it was Wesley. I tried to go out again because was here before me. This was just now, got rid of the stuff, started with lots of messages and stuff. This morning, probably not gonna be part of that.
See, whatever Archer is, there's a whole roll. 329. That's 3X low pro, 3X low pro.
I was sitting on the
Well,
west.
that's scoring the 91.
I was sitting on the west.
Yeah, yeah. Review.
They got some stuff. Goes over your muffler.
We missed all the simple stuff and now we're getting into like
It does.
advanced stuff, so maybe it's good,
Awesome.
yes.
Yeah, that might be.
We all want it to be.
Yes, the stuff you missed, you probably could have figured out right.
Well, I would like, I'm
And I
not
had
sure for it myself.
pre-read some of
That's
this.
okay, and I did, and reading this too, so.
They want to do things like regulations. I've changed it.
Sit down for a second. If you can sit down, sit down. If you can lie down, lie down. You get your one favorite.
What is that quote?
Yeah, Willie Mays.
So,
Feels like, and he was a pretty good athlete, so, you know.
I'm gonna get. $500 would be one. See, ain't no step for a stepper. $2,000.
Waste your effort.
123 for that one spares. What is? It's a rivet tool, there's a tool for punching out, and there's a tool for rivets in it. But like, I don't see. Yep. Set up. Oh, there it is, 3/404 rivet cut. It's a different pitch. It's longer between. You go ahead and buy that. I'm out. For 100 feet. Oh, sorry. Your bar is so 6 feet for minimum of 6, so you can make 15 chain. You make 15 chains.
If they're going $50 a piece, price.
I'm sorry, 50.
So chains.
What?
No,
Right?
maybe that's $50.
50.
Sorry, I set up the screen like.
$40 for each chain.
Okay, cool.
6 chains.
It's something else.
Marty was saying,
Thanks for keeping an eye on it.
There's 6 feet.
Yeah.
Yeah, 6 feet.
What issue we have?
We don't have to break out.
The working street.
They don't. How much is? Oh, yeah, so then, you know, right, it's gonna teach here and. Okay.
14 driving.
Yeah,
So
sorry, I didn't think about that.
There's gotta be some way
you
to.
gotta go.
Yeah,
They're
they're just.
So step and go.
Figured out, so maybe before we figure it out.
Yeah.
There they are with their.
Other than then, I don't, we may not need it as much because like, you know.
Well, let's go.
Figure it out, so.
Those semi chisels.
Well, they don't.
Meat. With the completion.
Okay.
Or.
Yes, we've been
It's not a.
slowly building up from simple to complex. So now you're getting here right when the real exciting stuff is about to start.
Okay,
Yeah.
So what, simple stuff, with me, media, linear, or whatever.
Yeah,
And, like mice, they have something in the same learn, different.
okay,
Where you can do opposite, computing,
Yeah.
I think that's what mice might say.
yeah,
There's
so
no-
now you
I'm sure
create
it's another model.
multiple imputed data sets and then it integrates with the actual model fitting packages to
Especially.
incorporate the uncertainty from the imputation into the computational degrees of freedom and stuff of the final model.
So I think that's what I heard of. And they said they can do that with. Like, that's what it's very.
Yes. Yeah, mice also have to.
Yeah, so it's like I learned, as far as full.
I need to learn that myself. Alrighty, well, thanks. Okay, we'll talk about
Because
that.
even just to get into your hydraulic,
Manual.
All right, everybody,
That was me.
chainsaw specs, you can talk about that,
We talked a lot about that.
Yes, yeah, sure, I mean, you need
Well, I've done the chainsaw
Yeah, I
for 3
bet.
weeks now.
And
I bet.
think I'm ready to retire after this meeting that we had.
I don't blame you. I wish I could.
Well, but one of the things that Lindsay is that these working groups that we have, they don't fit what the OMP is looking for.
Right, right.
So,
And it's gonna be a lot of hangers on. You aren't actually gonna work. And it's gonna be like any group project.
yeah,
I kind of want to know what went on in the wall there, but I'll ask you about it later. Okay, yeah, let's get back to, we've got another, just about a little less than an hour, and now we kind of did all the boring stuff, and now comes the actual interesting stuff, so, yeah. On our journey from simple to complex imputation methods. So, we've so far, our imputations have used information from within a single variable, like we only use information in the weight column to predict. Yes, Dan,
I'm sorry to interrupt, but just
Go.
before we go off, I just, because
yeah,
that random substitution one was really bugging me.
okay,
I think, but you would only use that in a massive data set, and realistically, right?
yeah,
Small
I mean,
data set, that's gonna,
it can be used in a modest sized data set, which we're going to do that, something that's basically a modified version of hot deck imputation, and then look at the influence on the results on a pretty small data set, so you'll be able to see how it influences.
I guess
Yeah,
when you use random, you're not.
you're not biasing, hopefully,
Well, the distribution.
If you get
won't
unlucky.
change.
with your randomness, though. Anyway,
Right.
Go ahead.
so that's what you're anticipating, yes, that's why we use multiple imputation, because it will do many
A bunch of
random
times.
draws. If
Gotcha.
one's unlucky, it will average over that. Yeah, awesome. Yes, so let's say we don't just want to use information within the weight column to impute. We want to use other information from other variables in the data. You know, if weight has correlations with other variables in the data set, we can figure out that correlation for the ones where weight or whatever is observed and use that information to impute values that we don't know the weight for. So we're going to go back to the Leafhoppers JASIDS data set for the next couple of examples here. See, I may have some, sorry to constantly be going back and forth here, but I may have some slides that might be useful for this. So let's skip forward here. Yeah, so yeah, like that's what I just said. We're going to do a regression using the complete rows from the data and use the coefficients from that regression to predict the ones where things are missing in and in each case, the variable we're trying to impute is the dependent variable, even if it's not our ultimate outcome of interest, it's the dependent variable in the regression used to predict its missing values. We're going to start very simple and just do a single bivariate regression. Like, let's say it's reasonable to assume that the minimum temperature and maximum temperature for a given observation are going to be positively correlated, right? So let's say in the JASIDS data set, we had some days or observations where one of the two was missing. So let's say we're going to use minimum temperature to predict maximum temperature. Even though, right, those are not the outcome of interest in our data set. The outcome is leafhopper abundance, but we're gonna, for now, make max temperature the Y variable and min temperature the X variable. And remember, if we do this right here on the JASIDS data, it's going to do complete case analysis for us by default and only fit the linear regression to those rows where we know both the maximum and minimum temperature, right? So we're going to do that. Using the LM function. Temp max is our Y and temp min is our X, and JASIDS with missing values is the data frame that we're going to get those variables from. So on line 199, you control enter. Okay. And then we can use the function coefficients to look at the slope and intercept that we estimated there. We can hit control enter. Okay, and you can see there's a slope. Well, the intercept is 25 and the slope is positive number 0.2. So for every 1 degree increase in minimum temperature increases by 0.2 degrees, right? That's what that means. Is that a good prediction? Well, one way we can look is by looking at the fit statistics from the regression. I didn't put this on the worksheet, but if you type summary, parentheses, and then the object is called temp_linear. And if you start typing something and then hit tab, it will automatically complete the name of that variable for you. We'll call summary on that. Hit enter there. Here you can see it is statistically significant, so that's good, but the multiple R squared is only 0.23. So it's like, well, this isn't really, there's a lot of information in maximum temperature that is not explained by minimum temperature. So this is at best a very crude approximation of the maximum temperature. But that's in this case, we're forcing ourselves to only use one other variable, so that's the best we can do for now. And now what we're going to do is use the predict function, which we've already seen before, which is to get predicted values from a linear model, and then plug them in to our data frame. Well, actually, I didn't plug it into the data frame. I just created a vector of imputed values. So first, we're going to say predict. And we're going to use this linear fit object, and then new data means which X values are we going to pull from. And we're going to use the entire JASIDS data frame to pull from. And we're going to call that pred temp max, the predicted values of max temperature. Escape there to dismiss that. And then we're going to create a vector of imputed values. Again, I'm doing this all by hand, longhand, just as by way of illustration. This isn't really, there's more concise ways to do this in your actual workflow data, but this is just to illustrate. So we're going to use the if-else function. Again, the first argument is this thing missing or not? And what function do we use to say is something missing? Can anyone tell me? We've used it many times today. That's correct. So if the temp max column is missing, that means is.na. If it's missing, first argument is what do we do if that's true? We're going to pull from the pred temp max, pred underscore temp underscore max. I can hit tab to complete that. If it is not missing, we will use the temp max column from our original data set to get the best. So we'll only use the predicted value if we have to, right? So we'll use temp underscore max column there. And that's going to create the imputed temperature value. Hit control enter. So now we have a completed vector where we filled in the missing values with ones that we imputed using the value of minimum temperature. The next two lines, you don't have to fill in the blanks for. Again, this is going to create visualizations. So first we'll make a histogram. You can see here are the, temp max has a very skewed distribution. There's not that many missing values. So like the distribution is maybe similar for the imputed versus present values. But then let's look at the scatter plot. So you can see there's still some missing values, right? We get a warning message that there were still some missing values because some of the rows in our data frame did not have minimum temperature. We were unable to predict maximum temperature in those cases. But we did, but those didn't have missing values for maximum temperature anyway, so the warning only applies to this plot is unable to produce a maximum and minimum temperature plot, but we filled in all the values. So you can see they're all right on this nice straight line, right? And that seems like a decent approximation for the most part, except that the relationship doesn't really seem linear anymore. Once you get to these high temperatures, the max temperature is going up at a much higher rate than the min temperature. But if we just use this simple linear regression, fails to capture that. So like this imputation is maybe not so great because when we observed min temperature of 25, the max temperature was way up here. But if you just use linear regression to impute, you're going to possibly underpredict there, right? So, okay, fine. Well, what can we do about that? Linear models are kind of like old school. What if we used machine learning, got fancy to use random forest or some technique that can pick up nonlinear relationships in the data? And not only that, it doesn't just use one variable to predict the missing one. It uses all the other variables as potential predictors in the data set. So we're going to, again, I'm just going to use a package called MissForest that has this random forest imputation built into it. And we can, what this does is it just allows you to take a data set that contains missing values, pass it in, and then it uses its own secret sauce random forest algorithm to take information from all the other columns in the data set to impute the missing values. Which is nice and easy, but we'll go into a moment why that might not be, it might be too easy and it might be problematic, but it is nice and easy. So again, we're gonna have to set the random seed because random forest algorithm includes randomness in it. So if you want to get the exact same results as I do, you have to set the random seed. So first hit Control Enter to set the random seed. And then I'm going to make an object called JASIDS RF imputed, standing for random forest. And the function is called MissForest, MISS capital F forest. And you could run that without any additional arguments, but I'm running it with one other argument. Variable wise equals true. And that just gives us a diagnostic report of the mean squared error for the random forest for, because I want to look at it. Variable wise equals true. Okay. Control Enter. And it takes a few seconds to do the random forest imputation. And the first, we're going to look at what does the imputed values look like. So the random forest imputed object returns a list with two objects. The first is a filled in version of the data set, and the second is the diagnostic output showing the mean squared error for each column. And the mean squared error are the errors in prediction for the ones that were not missing. So it's like it's saying if this algorithm predicts well the values we do know, it should give us decent predictions for the ones we don't know. But of course, we'll never know that for sure because they're missing. So we're just making the assumption again that the patterns for the non-missing values are similar to the missing values, which is now they don't have to be missing completely at random. They can be missing just at random and it will still work because it means we have the missingness depends upon other information in the data set. So we can, first of all, the first object in there is called ximp. If we type head parentheses our imputed object $ximp, it will give us a printout of the first few rows. So you can see it's just exactly the same shape as the JASIDS data frame, but it's got the missing values filled in as if by magic, but it doesn't tell us which ones are missing and which ones not. And this code you don't have to worry too much about exactly how it's set up. I just wanted to look at, I'm taking the square root of the mean squared error, which is called OOB error. That stands for out of bag, which is a term from Random Forest. OOB error. I hit tab and it completed that, the name of that missing of that column. And then I'm gonna name each one of those after the names of the columns so we can see which column is which. So some of them are 0 because those columns did not have any missing values, but the root mean squared error is basically the standard deviation of the prediction of the prediction error. So we have fairly high values for some of them, but like the temperature, if we look at the temperature one, on average, the square root of the squared error was about 1.3 degrees using the Random Forest imputation. And just out of curiosity, I wanted to look at what that very simple bivariate, just using minimum temperature, how well did it do in its root mean squared error? We can just calculate that manually, by longhand in R. By taking, first we'll use the square root function, SQRT, square root of the mean of the squared residuals, errors of the predictions. So residuals is the function there. So right, and you can see I put a squared after the residuals. It's the square root of the average squared residual. From our very simple, not super fancy machine learning algorithm that just used minimum temperature. Well, the root mean squared error there is 1.4. Our fancy Random Forest gave us 1.3. Is that really that much of an improvement? I would say not. It's 0.1 degree where we have a range of 10 degrees in temperature. So this just shows, again, it's a very small toy data set. There's not a lot of information there. And so you don't get a huge benefit from swapping to this more sophisticated method. And I've here's all right, we already made the plot for the linear interpolate or the linear regression imputation. Here I'm making diagnostic plots for the Random Forest imputation. There's the histogram, looks very similar to the linear one. And here's the scatter plot. You can see that we're starting to, it looks a little better because here where the distribution is more variable for maximum temperature, we start to see that it's getting a little more variable for the imputed values as well. It maybe isn't capturing everything that's going on, but it's starting to get there a little bit.
Yeah, and because there's some randomness there, when I look at everyone's results, they're different. So
Yes.
does that matter?
So now that is what we're going to be talking about for the last half hour of today, is using the, basically I would say most scientists that I know of, including myself, I must confess, do a lot of ad hoc imputation methods with just whatever they think of at any given moment. Like maybe we'll substitute the mean for a few missing values, or maybe even something fancy like this Random Forest imputation. What they want is a nice, tidy looking, perfect data set that doesn't have any missing values in it. It doesn't have any ugly, empty gaps. Then we fit our statistical model, test our hypotheses, and publish a Nature paper on that. Super. But there's a problem with that approach, which is the fundamental issue there is if anytime you have a value that you're using as data that you didn't directly observe, it is not data, it is a prediction of a model, right? Like this, even if it's a simple model, like using the mean to impute all the way up to this Random Forest thing, these are not actual observations. They are the result of a prediction from a model, and models inherently have uncertainty in their predictions. And whenever you just do a single imputation, and use that as if it were data, you are ignoring any uncertainty from that process in your final results, which can give you, well, it can, if there's bias, it can give you the wrong answer. And even if there's not bias, even if the data are missing completely at random, it will give you artificially precise estimates of the uncertainty in your result. The confidence intervals will be too narrow for what they really should be if you accounted for the fact that you actually were, some of your values aren't really data, they're only imputations, right? And yeah, that's the case from simple mean imputation all the way up to fancy random forest, whatnot, if you don't account for that. Let's see, I think I have slides that should that. I put a, oh yeah, I hate all this uncertainty, as Rex from Toy Story like to say, we don't like uncertainty and we're trying to just sweep it under the rug, but actually we should embrace the uncertainty. And yeah, so the developer of the mice package that we're going to be talking about, Stef van Buren, he said, basically, regression imputation artificially strengthens the relations in the data. Correlations are biased upwards. Variability is underestimated. Imputations are too good to be true. Regression imputation is a recipe for false positive and spurious relations. But I just explained to you how to do regression imputation. So why did I do that if it's really so bad? Well, it can be okay if we account for the uncertainty in it properly. So that's what we're going to talk about for the last half hour. Again, this is just scratching the surface of this complex topic, so you'll have to just consult with me later if you really want to delve into this in detail. Yes, multiple imputation. And everything that we've done so far, with the exception of hot deck and I guess the random forest imputation, were deterministic. They turned a missing value into a single imputed value. And then if we go ahead and use that completed data set as our data set for analysis, it's not carrying that uncertainty forward into our final estimate. An attempt to solve this problem is the technique of multiple imputation. And again, we mentioned Donald Rubin before. He kind of is the godfather of this technique, and it was his insights that led to later developments in multiple imputation. And his idea was that you should, which was sort of controversial at the time, but now is very highly accepted, is that what you need to do if you are doing imputation is create multiple imputed versions of the data set, and in each case, draw the imputed values from a distribution, and which can be created in many different ways. But the basic idea is that there should be, since the data is missing and we don't know exactly what that true value is, there should be a probability distribution associated with that missing value. And we can draw values from that many times. Every time we do that, we fit our statistical model to that imputed data set. And then there has to be some process for combining the estimates from those models fit to each of the imputed data sets into a single final estimate that incorporates the uncertainty due to the imputation. And yeah, there's formulas that they developed for actually adjusting the degrees of freedom, which affects the confidence intervals and p-values accordingly. And Rubin and other people later found that you really don't have to do that many multiple imputations to get a good result. You can do about 10 is actually fine for most cases. So if you have some very computationally intensive model that you have to fit to each imputed data set, you don't have to do it hundreds of thousands of times. Actually, a fairly small number usually gets good results. Simulation has shown. What are we going to use to do this? In the last little bit of time we got, we're going to use the MICE package, which stands for multivariate imputation using chained equations. And Teddy has told me that similar methods exist in Python in the scikit-learn package. I don't know exactly how they're implemented, but yeah, that would be one to look into if you like Python. The cool thing about the mice package is that it allows you to incorporate the multiple imputation into your existing statistical analysis because it has methods that integrate with other statistical model fitting packages in R. So like whether you use LM, GLM, or if you're doing mixed models with mixed model fitting, or even Bayesian mixed models with BRM, or if you use the EM means package to estimate treatment means and compare them, all those packages interact with the mice package, and the results they produce, if you feed the mice output into them, will incorporate the uncertainty due to the imputation, and it'll just automatically correctly adjust the degrees of freedom and give you results that account for the uncertainty in your imputation. Yeah, so here's the basic workflow is we use the mice function to create some number M of imputed data sets. And that's where you would pick the imputation algorithm that you're going to use. There are many, right? Like if you want to use hot deck, if you want to use linear interpolation, if you want anything we've talked about so far, that's where you put that in, but you'll do it multiple times. And then obviously, if you just impute with pure linear interpolation, there's no randomness there, so they'd all be the same. So the algorithm should incorporate randomness into it somehow. And then that produces an object of type MIDS, which stands for multiply imputed data set. We're going to show an example of this in a minute. Then you basically take the function width, and inside of that fit your statistical model, and that will fit the model to each of the imputed data sets. And that will create an object of type MIRA, multiply imputed regression analysis. Then there's a function called pool, which then combines the estimates from each of those data sets into a final estimate of the parameters of the model, which creates a MIPO object, multiple imputation pooled object. Yeah, or you can just pass the MIRA object directly to EM means or other functions, and it will combine the estimates in there. Yeah, so let's do that. And I'll explain what all the defaults are, or some of them, in a second. But let's just do an example. So let's say we're going to take the JASIDS, the leafhoppers data frame, and we're going to create 10 imputed data sets. We're going to use the mice function. First argument is the data we want to impute. Everything else is going to be default except m equals 10, means we're going to do this 10 times. And I'll explain in a minute what it's doing. And then random seed, I put in my zip code here so that you can get the same results that I do. Again, because the algorithm involves randomness. Mice is the function. There's the name of the data. And the only thing we're specifying here besides the random seed is m, the number of imputations, equals 10. And it says PMM, it's the default algorithm it uses is called predictive mean matching, which I'm about to explain what that does. But first we'll just run the code, hit Control Enter. Okay, it prints some progress indicators there. And then here, I'm going to be just printing out some of the objects within the output of the JASIDS mice imputed. The first one is nmiss. So I'm just going to print that one out. That just tells us how many missing values there were in each column, right? And then the imp object within the list of output from JASIDS mice imputed. You can see it produces a bunch of output if you scroll up. It has as many elements in it as there are columns in the data frame. Some of them are an empty object because JASIDS column had no missing value, so it didn't have to do any imputation. But the RF variable had 4 rows that had a missing value, right? And there are the row numbers, and then here are the 10 imputed values for that particular row for that variable. Right, and then temp max had 12 missing values. So here, row 3, it imputed, every time it did an imputation, it got a different value, right? because there was some randomness involved. And let's see, where's my mouse? Yep, and then it will tell you what method was used for each column. It's PMM, predictive mean matching. So I think I have some slides that explain what it was doing there. Yes, so this is the default algorithm used by mice for continuous numerical data. Okay, I'll just kind of broadly explain what it does. It fits a ridge regression, which is a kind of semi-machine learning version of regression using the other columns in the data set to predict the values for other data points in the column. And then, but it doesn't just use that ridge regression prediction to impute. It just uses that ridge regression for each missing value. It finds a small number, by default 5, but you can change that. Other observations in the data set that have the most similar predicted value to that one. Then it takes the actual observed values for those similar prediction values and randomly picks a value from them. So if you can think back, this kind of combines aspects of regression, machine learning regression imputation with hot deck imputation. It uses a regression, but only as an intermediate step to figure out which of the random values from the data set we should pull. So it's kind of like hot deck plus regression imputation. That's the default algorithm it uses. And again, this algorithm has different parameters, like especially the 5 number that is used to as which like nearest neighbors are, how many nearest neighbors you're pulling from, can be tweaked and get different results. Yeah. The 5 number was not chosen arbitrarily. It's chosen because it has good performance in a variety of cases. But with this and with anything else, you shouldn't just blindly follow the defaults of packages all the time. You should look at them and possibly modify them based on what works for you. So yeah, don't just assume that the developer of the package made perfect default arguments of the parameters that will work for every single case, right? That's just a good lesson anyhow. Yeah, so that's the I'll just run that so you can see. I made another custom function to plot the results of multiple imputation. And so here's what it looks like for minimum and maximum temperature. Yeah, it gives some warnings, but we can ignore them. They're just related to the plot. So and you can see now for the first time, I've put some error bars on the imputed values, right? So this is in my code, this is the range between the minimum and maximum of the 10 imputed values for each of those places where temperature maximum was missing. And this circle is just a median of them, but there's not one single imputed value. I just plotted that so you can see the median. It's really just 10 values that it's imputed. That's just the one that happens to be in the middle. But you can see that it actually makes sense in a way, because here the range is smaller where the variability in the underlying non-missing data was smaller. But when you start to get to these places, we get a much wider error bar, which actually makes sense. So there should be more uncertainty here because there's not as much information, because we're sort of in this area where there's more variability in the data in the underlying data. Yeah, so that is the first step of mice, right? We have now made a multiply imputed data set. What if we wanted to actually predict the leafhopper abundance using our environmental covariates, all of which had missing values filled in, and then incorporate the uncertainty in that estimate into our final conclusion? How would we do that? Here. Yes, so we're going to use the with function to do that. With means take the first argument and then within that perform some perform some computation. And if you pass a multiply imputed data set as the first argument, it will interpret that as run whatever statistical model is in the second argument for each one of those 10 imputed data sets separately. And what we're gonna run a very simple multiple regression using the LM function. And the Y variable we're trying to predict is the JACIDS abundance, which for whatever reason has a capital J in the underlying data. So you got to put capital J, JACIDS. And yeah, this may not be a good model in real life, but I've just taken all the environmental covariates and thrown them in as predictors in a multiple regression to see if we can take these 7 environmental variables and use them to predict the abundance of leafhoppers in Maharashtra region of India. So we'll hit Control Enter to run that. And that creates basically an object that contains 10 regression fits. 10 regression fits to each one of these imputed iterations of the JACIDS data set. And how do we combine those 10 into one unified estimate? We use the pool function to do that, which pools the estimates from each of those 10 regression models into one final set of estimates. Hit escape there. We'll enter. And so it's done that. And then if we call summary on that. So I realize I just skipped some code above there. I'll go back to that in a moment. But here, we'll use summary. And yeah, so here you can see the output. We get a estimate for each of the coefficients. So here's the intercept of leafhopper abundance if all environmental covariates were 0. And then here's like, you know, as minimum temperature for each 1 degree increase in minimum temperature, we get a 0.39 increase in whatever units leafhopper abundance is measured in. Yes.
You have a question about why the error bars are so large?
For this plot here?
Yeah.
Yes, so that is because this is the uncertainty in the imputed value of maximum temperature for this particular data point. I've only plotted it against minimum temperature, but other information from other variables will use to predict that. And it just means that that is sort of in a region of our multivariate space where we don't have a lot of information. It's sort of a more unique combination of environmental parameters that doesn't have a lot of nearby data around it. If it had a lot of nearby similar values, we would have less uncertainty in the prediction. That one is kind of toward the edge, so it's got more uncertainty, which is good. Like that's actually what we want. Like it's good that we're correctly accounting for that. You know, it would be yeah, that is more honestly accounting for the fact that there's more uncertainty in that prediction than there is for the prediction here that's kind of right in the middle where we have a lot of dense information around it. Yes, and I skipped around in the code here a bit, but I just wanted to show how you could use different algorithms inside of mice besides the default predicted mean matching. Like you could use the RF method as well to do random forest imputation, but it will. Last time we did the miss forest, it just gave us 1. This time we're going to do, since random forest. Also, the random forest algorithm in mice is not just a straight random forest. It also, they have their own algorithm that again uses like a somewhat of a tweak on the hot deck method to use random forest to produce the nearest neighborhood that is that we use to draw values from and get imputed values. So let's I just want to do that as well, and then we're going to compare the performance of those methods. Method, so you can use the method argument to change up what algorithm is used to impute. And again, we're going to use the same 10 imputed data sets and put in a random seed so you can get the same results as me. Method equals RF in quotes. Control enter there. So I just scrolled up a bit in the code there. Hopefully people followed that. We're back on line 238. Control enter. It takes a couple of seconds, but we're done already. And then, and here's just my little custom function. So yeah, here the random forest produces an even wider uncertainty interval for that particular observation that people were commenting on last time. So yeah, maybe this is unreasonably large, but that's what that particular algorithm is giving us. So let's and then I also wanted to use the random forest imputed version of the data set, those 10, to do the same linear model with all the covariates and then pool those estimates. So let's do that as well. So I called this, it's called JASIDS mice RF imputed. So going down to this line, we're going to take that random forest imputed version and do a multiple regression on it. JASIDS underscore mice. Yeah, so then I'll just go down in here and hit tab to complete that. We're taking the random forest imputed 10 data sets, doing the linear model on each of them. On that, and then we'll use the pool function to combine across those 10 imputed data sets and get coefficient estimates. Control enter. And then we will hit control enter on this summary line. And here, yeah, it also gives you combined estimates, but it's just by looking at it, I don't know how well they did compared to the other ones. So the next few lines, yeah, this is a visualization, so you can see it, but you don't necessarily have to run this on your own machine. I'm just going to run it. I basically, this is just some code I made to combine the pooled estimates from the predictive mean matching one from the random forest one. And then I just did a complete case analysis where I just took the 33 rows that didn't have any missing values and did the multiple regression there. So like doing the one where we just delete missing values. Got the confidence interval on all the parameter estimates there, and then plot it next to each other so we can see how we did. I'm gonna run that. Okay, so here, our red ones are the complete case analysis, the sort of naive way where we just deleted the missing values. We didn't do any imputation at all. And then the green and blue are the two different imputation algorithms. So I think for the most part, the two imputation algorithms agree with each other reasonably well, and in many cases don't give that different of a result than you would get from complete case. Because again, the data are missing completely at random, so it shouldn't produce a lot of bias. But you know, there are, like, especially in this wind velocity one, if we did the complete case analysis, the parameter estimate is close to 0 and the confidence interval overlaps 0. But if we do the imputation, we actually get a negative relationship that may or may not be statistically significant if you look, or at least it's close if it's not. And these are 95% confidence intervals. And yeah, slightly different magnitude, but they're both much more on the negative side than our naive analysis. And that's possibly because just due to random chance, the observations that were driving that negative relationship got deleted from the data set, but we've been able to recapture that relationship through imputation. So that actually shows a possible, yeah, we wouldn't bother with all this imputation stuff if it didn't affect the outcome. So sometimes you actually do get a different conclusion with or without it. Yeah, so at this point, we have until 12:30. So I have a couple more examples with mice, but to be honest, I think it's not going to benefit you that much to go through them because you've now seen this stuff in action and you can read the rest of the lesson on your own time as well. I'll see if there's any other information I can drop pearls of wisdom on you before we take a couple minutes, if there's any questions, but yeah, oh yeah, you can also use mice for the non-random imputation methods, just like linear interpolation or imputing with the mean. They're all available in the method argument. You just look in the documentation to see that. But then you would just set n equals 1 if you're just going to do those simple non-random imputation methods, and it'll give you that single. I did them all longhand so you can see how they're done, but you could actually just do them all within the mice package if you wanted to. Yes, we already did that. And yes, basically, the last 2 points I was going to make, which I won't go through the examples in the interest of time, is that there are also methods in mice that work with multi-level data, with data from different blocks, and it will actually take into account the repeated measures relationship in the data or like correlations of data points within replications and stuff to do imputation there, which can be helpful. And yeah, the code for it is kind of weird, so I'll save that for people that actually need it. And the last point I wanted to make is that basically multiple imputation is kind of like a Bayesian technique. If people are familiar with Bayesian statistics, it treats parameters and unknown values being another parameter of the model as drawn from a random distribution. That's exactly what multiple imputation is doing. So we're kind of doing already a little bit of Bayesian statistics every time you do multiple imputation, but you can actually use mice with Bayesian mixed models as well and pool the estimates with the R package BRMS, which is basically just a Bayesian version of the regression models we've been doing. And the example you can read in the text version of the lesson shows that you get very similar results to what we got using multiple imputation without Bayesian model, because we're already doing a little bit of Bayesian stats when we do multiple imputation. Yes, and there's also another way of doing Bayesian imputation, which is instead of doing this two-step process where you first do multiple imputation, then fit the model, you can actually do it all in one and like explicitly write out your missing data model within the Bayesian model, all in one model, and then it kind of treats the missing values as parameters in your model, and you can set prior distributions on them. Honestly, I think it's like the most elegant way to do it, but it's honestly a lot of work and hardly makes a difference in most cases. So I'm happy with the two-step approach of doing multiple imputation and then throwing a Bayesian model on top of that. The only reason not to would be if your model is extremely computationally intensive to run. You'd have to run it 10 times if you did 10 multiple data sets. But if it's this way, you only have to fit one model, which can, yeah. So only if you have like a really gnarly model would this be worthwhile. Again, that's just a point if you ever need it in the future to talk about. So yeah, that's all the material I have. And if you go back to the website, you'll be able to read the full text with a lot more notes and details. And I also put in, if you want to do homework, like if you hadn't have enough of this, I made some homework problems with another fake data set that you can play with. And there's some exercises there. And I also included links to further, let me actually, why don't I just show that to you real quick? And there's also a survey. If you're doing other ones this week, you can just wait till the end of the week to fill out the survey. If you scroll down the bottom of the Mississippi 2026 page, there's the survey. And then just to show you if you go to the text version of the lesson, and we'll go all the way down to the bottom, there's here's some additional resources, some other packages I didn't discuss, which are useful. And then There's some books, ebooks and other tutorials on missing data that are really good that I recommend, looking at. And then there's some homework, with answers if you want it. Yeah, so there isn't a whole lot of time for questions, but does anybody have any questions before we adjourn here?
Just to clarify, you're
Yes.
gonna be in person, you're gonna be at Stonewall tomorrow?
That's right. So yes, tomorrow, I'm driving to Stoneville, tonight, and then tomorrow morning at 9, I'm going to be giving just like an hour talk on experimental design, but it's not like a hands-on thing. It's just a one that you can listen to if you want. And then on Thursday morning, also in person there, I'm doing, a workshop, similar format to this, but we're gonna be talking about very basic intro to machine learning, and how it works. Which I've done before, like remotely, so people may have already had that one, but, yeah. That's what we're doing on Thursday, and it'll be on Teams as well for y'all if you want to participate. Yeah, thanks to all of you for, being such good learners. I appreciate it. I will stop the recording now.
Just one last question. How do you address the error messages that you get it in R? How do you understand the language? Is there an easy way to understand and fix it yourself?
So just generally what to do if you get errors in R.
Thank you.
Yeah, I mean, I think, you know, the traditional way of doing it was to copy and paste your error message into Google and see what you get. Now people would probably copy and paste it into a large language model and see what it says, which is a glorified way of doing it in Google. But, yeah, I think it's something that comes with experience because, you know, I was confused by the error messages the first time I saw them as well. And most of them do crop up in the documentation as well. So looking at the documentation helps and yeah. Mostly, you know, and then oftentimes if you Google it, it will bring, a lot of these packages have GitHub pages where people have filed bug reports in the past, and reading those often looks at the same issues that you have. So that's often where you can find information about errors. But yeah, I think with practice and with experience, you'll start to learn how to diagnose these things. And there's sort of common typos too that you know, syntax errors are called by like wrong capitalization or punctuation and things like that. Yeah.
Thank you.